GCE Advanced Level Chemistry Practical Series, Experiment number 13, Identification of Halides. The aim of this experiment is to develop the skills of identifying chloride, bromide, and iodide. These are halide ions. So the aim is to identify these ions when they are existing separately in solution. So the aim of this experiment is to learn the skills that are required to identify these ions when they are present in different solutions. Introduction. In this experiment, we will use reagents such as aqueous silver nitrate, aqueous lead acetate. Now, instead of lead acetate, we can use lead nitrate as well. Chlorine water and concentrated sulfuric acid for detection of chloride, bromide, and iodide ions in an aqueous medium. So, we'll be using all of these solutions and we'll learn about the theory and then later on we'll experimentally see how we can use these aqueous solutions such as silver nitrate, lead acetate, concentrated sulfuric acid, chlorine water to identify the presence of chloride, bromide, and iodide ions. So students, if you take a look at the 17th group of the periodic table, elements fluorine, chlorine, bromine, iodine, acetine, these elements that are found in the 17th group of the periodic table are known as halogens. And as these halogens form ions, they are known as halide ions. So halogens will usually gain one electron and form 1 minus charged ions. So those ions that are formed, F minus, Cl minus, Br minus, I minus, At minus, these ions are known as halide ions. And their names will end with IDE. As you know, all the anions, monoatomic anions, usually end with the name IDE. So we have fluoride, chloride, bromide, diacetyl. So out of these halide ions, we are going to focus on identifying the presence of chloride, bromide, and iodide ions in this experiment. Now in this slide, students, we are going to observe the chemicals and equipment we will be using for this experiment. So over here, what you see are the equipment that we'll be needing, and over here we have our chemicals. So students, when you are trying to conduct an experiment where you try to identify the presence of chloride, bromide, and iodide ions, you would need solutions containing these ions. So we can form different solutions using salts of sodium that has chloride ions attached to it. So basically sodium chloride solution, or potassium chloride solution, or ammonium chloride solutions can be used to introduce chloride ions. Or when it comes to other ions as well, bromide and iodide ions, we can use their sodium or potassium salts or ammonium salts to obtain these aqueous ion solutions. So through their sodium, potassium, or ammonium salts, we can introduce chloride, bromide, and iodide ions into an aqueous medium. So we will have these salts of chloride, bromide, and iodide ions, and then we have silver nitrate solution that we can use to identify the presence of halides, concentrated sulfuric acid, and we learned we need lead nitrate or lead acetate. You can use either one in this experiment. Chlorine water, chloroform, or carbon tetrachloride. So these are organic solvents, right? Organic solvents, you can use chloroform or carbon tetrachloride for this experiment. Dilute ammonium hydroxide, dilute nitric acid, and starch solution also can be used in this experiment. So these are the chemicals that we'll be using for our experiment. Let's move on to the next slide. Now in this slide, we are going to learn how to identify halide ions using silver nitrate and dilute nitric acid. Take about 1 cubic centimeters of halide solution separately into test tubes and add silver nitrate solution a little at a time and observe whether a precipitation occurs, and then add dilute nitric acid. So students, we are going to take solutions of sodium chloride, sodium bromide and potassium iodide separately into 3 different test tubes. And in each of these solutions, since these are ionic compounds, sodium and chloride ions will be separated in the aqueous medium. So we have free chloride ions available in sodium chloride solution. And when it comes to sodium bromide solution, we have free bromide ions. And in the potassium iodide solution, we have free iodide ions. So these iodide ions are now freely available in the aqueous medium. And then when we add silver nitrate, now silver nitrate is an aqueous solution. So therefore, in this particular aqueous solution, we have silver 1 plus ions and nitrate ions available. So when we add silver nitrate into a chloride ion solution, silver 1 plus ions and chloride ions will come into contact with one another, and as they react, they will form silver chloride. And silver chloride is a water insoluble precipitate. So you can see over here, sodium chloride when added with silver nitrate, it will form silver chloride. It will form silver chloride, which is a white color precipitate. Very important, which is a white color precipitate. And as you can see, we have indicated the fact that it is a white color precipitate here. So it will collect at the bottom of the test tube once you add silver nitrate into a solution of sodium chloride. And as soon as you add it, actually you will observe the formation of a white color precipitate, which will get collected at the bottom of the test tube. And then we have sodium bromide reacting with silver nitrate. Again, in sodium bromide solution, we have bromide ions. Silver nitrate solution has silver 1 plus ions. So silver 1 plus and bromide ions will come together. When we react them together, we form silver bromide. So silver bromide is again a precipitate. It is not soluble in water. It's a light yellow color or pale yellow color precipitate. So you can see in this diagram as well, we have a pale yellow precipitate observed. And that pale yellow precipitate that you observe over here is our silver bromide. And when it comes to potassium iodide solution, we have iodide ions in the medium, and as you introduce silver nitrate, silver 1 plus ions that are introduced into the medium will come into contact with iodide ions and will form silver iodide. Silver iodide is a yellow color precipitate. So you can see AgI, which is water insoluble yellow color precipitate, will be formed, and you can observe that precipitate at the bottom of the test tube. So it will take some time for the precipitate to get collected at the bottom, but you can see the formation of the precipitate as soon as you add silver nitrate into your potassium iodide solution. So these are the observations, students. As you add silver 1 plus ions or silver nitrate solution into a halide ion solution, if chloride ions are available in that particular solution, you will see the formation of a white color precipitate because silver chloride will be formed. Silver chloride is white. And if you add silver nitrate to a bromide ion solution, a very pale yellow color precipitate will be formed because silver bromide precipitate is formed and silver bromide is pale yellow color. And if you add silver nitrate into an iodide ion solution, you will be forming a yellow color precipitate. This is not going to be a very strong yellow color precipitate, students. Somewhat of a lighter but more darker yellow color than silver bromide. So a yellow color precipitate will be formed when we add silver nitrate into an iodide ion solution. So silver iodide is going to be formed, and you can observe this color when we conduct these experiments in the lab. Then we move on to testing these precipitates with nitric acid. So we are going to add to these precipitates that we formed, we are going to add dilute nitric acid. So what will happen when we add dilute nitric acid into each of these precipitates? You will not observe any change. In the presence of dilute nitric acid, silver chloride, silver bromide and silver iodide precipitates will not dissolve. They are not soluble in dilute nitric acid. So they will not dissolve and you will not see any change. You will not observe the precipitate dissolving when we add dilute nitric acid into each of these precipitates. Now in this slide, students, we are going to look at how silver bromide is going to react when we add dilute ammonia and concentrated ammonia, and how silver iodide is going to react in the presence of a dilute or concentrated ammonia. So one thing you should keep in mind is when you react silver bromide with dilute ammonia, silver bromide will not dissolve in dilute ammonia. However, in concentrated ammonia solutions, silver bromide will dissolve, but in concentrated ammonia solutions, silver iodide will not dissolve. So in order to dissolve silver chloride, a dilute solution of ammonia was sufficient enough, but when it comes to silver bromide precipitate, to dissolve silver bromide we needed a concentrated ammonia solution, and when it comes to silver iodide, even a concentrated ammonia solution will not be able to dissolve silver iodide precipitate. So the information related to that is given over here. If you take ammonia solution and then add it to silver bromide precipitate, it will dissolve if the ammonia is concentrated enough. So this will form a colorless aqueous complex. The same complex we saw earlier will be formed. One silver 1 plus ion will form 2 coordinate bonds with ammonia ligands and will form this ammonia and silver complex. When it comes to adding concentrated ammonia to light yellow precipitate of silver iodide, it will not result in dissolving the precipitate. Very important. It will not dissolve the precipitate. So silver chloride dissolves in dilute ammonia, silver bromide dissolves in concentrated ammonia, and silver iodide does not dissolve in even concentrated ammonia. The silver iodide precipitate is insoluble in aqueous concentrated ammonia. So this is a very important observation you should keep in mind. So we can take a look at the summary here. If you take a look at the summary, halide ions, when treated with silver 1 plus ion solutions, will form these precipitates: silver chloride white color precipitate, silver bromide pale yellow or cream color precipitate, and silver iodide will form a yellow color precipitate, a yellowish precipitate. And their solubility in aqueous ammonia solutions are given here. When it comes to silver chloride, it dissolves in dilute ammonia solutions. When it comes to silver bromide, it dissolves in concentrated ammonia solutions. When it comes to silver iodide, it does not dissolve even in a concentrated ammonia solution. So this is going to be insoluble in even a concentrated ammonia solution. The balanced equation for the reactions of halide with silver nitrate is given here. So you have sodium chloride reacted with silver nitrate here. So sodium 1 plus and chloride ions are present in sodium chloride solution. Silver nitrate contains silver 1 plus and nitrate ions. So when they react, we form silver chloride, which is the precipitate, and sodium nitrate. Sodium nitrate is colorless, so the medium will appear clear or colorless while forming a white color precipitate. Sodium bromide, when reacted with silver nitrate, will form silver bromide, a pale yellow color precipitate, and sodium nitrate. Potassium iodide, Ki, will react with silver nitrate to form silver iodide. So, what is the color of silver iodide? A yellow color precipitate. Like I mentioned earlier also, this is not a very strong yellow color. However, it appears to be a yellowish precipitate. So, you have a yellow color precipitate formed with silver iodide, and the other product that is getting formed in this equation is, in this particular reaction, is potassium nitrate. Potassium nitrate, as we introduced potassium iodide in the medium, we have potassium 1 plus ions and nitrate ions coming from silver nitrate together will form potassium nitrate. Potassium nitrate is colorless, so therefore in a clear solution or colorless solution, we will see a yellowish precipitate being formed when silver iodide is formed through this reaction. Identification of halides using lead nitrate and dilute nitric acid. So students, when it comes to halides, just like halides reacted with silver 1 plus ions, halides also react with Pb2 plus or lead 2 plus ions. So we are trying to introduce lead 2 plus ions into the medium where halide ions are present. So in the presence of lead 2 plus ions, halide ions will form different precipitates. So how do we introduce lead 2 plus or Pb 2 plus ions into the medium? Through a salt. So we can take lead nitrate or lead acetate. Both of them can introduce Pb2 plus ions into the medium. So we have used lead nitrate here. A lead nitrate solution to a solution in a test tube, to a halide ion solution in a test tube. Observe the color of the precipitate formed. Then add dilute nitric acid and note the observations. So as you add lead nitrate to a sodium chloride solution, sodium chloride has chloride ions, lead nitrate contains Pb2 plus ions or lead ions. They will come together to form lead chloride. Lead chloride is a water insoluble white color precipitate. It's a water insoluble white color precipitate. You can see over here a white color precipitate is indicated in the test tube. So as you mix sodium chloride and lead nitrate, very clearly you can see the formation of a white color precipitate. And then we have lead bromide formed when we add sodium bromide and lead nitrate together. You can form lead bromide. Lead bromide will also be a water insoluble precipitate. So now students, tell me, can we separately identify a chloride ion solution and a bromide ion solution with the use of lead nitrate or lead acetate for that matter? The answer would be no, because as you add lead nitrate to the chloride ion solution and the bromide ion solution, both of them will form a white color precipitate. So lead bromide and lead chloride are both white color precipitates. So separately identifying them would be difficult. So you can't use lead nitrate to separately identify between chloride ions and bromide ion solutions. Lead iodide, however, is going to be a yellow color precipitate. This is a very interesting reaction. As this reaction takes place, a very bright yellow color precipitate would be formed. So this yellow color precipitate will be indicative of the fact that lead iodide was formed. So as you react potassium iodide solution with a lead nitrate solution, iodide ions and lead ions will come together to form lead iodide, which is a water insoluble precipitate. However, if you heat any of these precipitates in an aqueous medium, they will dissolve. But when you are conducting this experiment at room temperature, when you add lead 2 plus ions with potassium iodide or iodide ions, lead ions and iodide ions together will form lead iodide, which is a yellow color precipitate. You will observe that this is in fact a very nice precipitate that we get. So we can use lead nitrate to identify the iodide ion solution separately from these two chloride and bromide ion solutions, because the color of the lead iodide that is formed is not going to be white. Solubility of the precipitates formed in an acid. So again, if you take lead chloride, lead bromide and lead iodide, these precipitates, and if you try to dissolve them in nitric acid, just like when silver halides didn't dissolve in nitric acid, these also will not dissolve in dilute nitric acid. Keep in mind, we were using dilute nitric acid. So in dilute nitric acid, these will not dissolve. So all of these precipitates are insoluble in dilute nitric acid. I hope you remember a little while back, I mentioned the fact that when you add water to each of these precipitates and if you heat it, then what happens? The lead halide precipitates that we spoke of today, which are lead chloride, lead bromide and lead iodide, these precipitates will dissolve if you heat these aqueous suspensions, or if you add water to these precipitates and if you heat the mixture, then these precipitates will dissolve in hot water. Add water to the precipitates, lead chloride, lead bromide and lead iodide, and then partially submerge them in a water bath. So if it is in a test tube, you can add a little bit more water if you want, and you can then place the test tube in a water bath to provide even amount of heat to the test tubes. All precipitates dissolve in hot water. So as the temperature of the solution in the test tube increases, then you will observe the precipitate that is found in our test tubes will start to dissolve. All of the precipitates dissolve in hot water to give colorless solutions. So we have lead chloride dissolving in hot water to form lead 2 plus and chloride aqueous ions. So these are both aqueous ions, meaning that they have now dissolved in aqueous medium. When it comes to lead bromide also, you will observe the same observation. They will dissolve in an hot water or in hot water to form aqueous lead 2 plus ions and aqueous bromide ions. So white color precipitates will dissolve when it comes to lead bromide and lead chloride. White color precipitates that were initially observed will dissolve as you heat the mixture. What about lead iodide? Yes, even lead iodide. Lead iodide, we observe a yellow color precipitate present in the lead iodide. You can see if you take it to a separate beaker and do this, you can see the lead iodide, a nice yellow color precipitate here. And if you heat this mixture, what will happen? This yellow color precipitate will dissolve to give us a colorless solution, not a yellow color solution, students. The resultant solution is going to be a colorless solution because we are going to release iodide ions and lead 2 plus ions into the aqueous medium. Lead 2 plus ions as well as iodide ions do not show a color in aqueous medium. So the colorless solution is for. So the resultant solution after this yellow color precipitate dissolves is going to be colorless. Now students, we saw how the precipitates dissolve when we heat these mixtures, and each of the precipitates dissolve to give us a colorless solution. Observation that you should keep in mind. And these solutions are still warm. If you allow them to cool down to room temperature, you will observe these precipitates that dissolved in hot water will get reformed as the solutions cool down. So when it comes to lead chloride and lead bromide aqueous solutions that are now present over here in hot water, as these solutions cool down, they will form needle-like precipitates or crystals of lead chloride and lead bromide. So these needle-like crystals or precipitates that are getting formed will have the same color as before. They are going to be white in color. So as these solutions cool down, the precipitates will get reformed, and as they get reformed, you can observe a slight needle-like nature of these precipitates. When above solutions are cooled, needle-like white precipitates will be formed in lead chloride and lead bromide solutions. So as these warm lead bromide, lead chloride solutions, they cool down. When they cool down, again the lead chloride and lead bromide white color precipitates will get formed, and as they get formed, they will show a needle-like crystal shape, or needle-like precipitate will be formed as they cool down. In lead iodide, however, a golden yellow precipitate will be formed. Lead iodide precipitates that get reformed do not look like needles as they get reformed when the warm solution is cooling down. So the needle-like white color crystals got formed when the solutions were cooling down in lead chloride and lead bromide, but lead iodide, we did not see the formation of a needle-like precipitate getting reformed. Instead, a yellow color solid precipitate was formed. Writing balance equations for the reactions with halides with lead nitrate, you can see sodium chloride reacting with lead nitrate forming lead chloride and sodium nitrate. So you can see lead ions and chloride ions. Lead ions from lead nitrate and chloride ions from sodium chloride will react together to form lead chloride, and the nitrate and sodium will react together to form sodium nitrate. And lead chloride precipitate is a white color precipitate. And when it comes to sodium bromide reacting with lead nitrate, lead 2 plus ions and bromide ions will form lead bromide PbBr2. Students, keep in mind the charge on lead ion is 2 plus, so it will be forming a precipitate after reacting with 2 bromide ions. So lead bromide is going to be also a white color precipitate, and a nitrate and sodium will form sodium nitrate. Similarly, iodide ions and lead ions together will form lead iodide, and the remainder of the ions will get together to form potassium nitrate. Lead iodide is our yellow color precipitate. So these are the balanced chemical equations for the reactions that are taking place when we add lead nitrate into our halide ion solutions. And over here, students, we come back to the same topic we discussed a little while ago, which is how the precipitates of lead halides are dissolved in hot water. So lead chloride, lead bromide and lead iodide precipitates will dissolve in hot water. If you add water to the precipitate and if you heat it, then at that point we will see the precipitates dissolving. Lead chloride will dissolve to form aqueous lead 2 plus ions and chloride ions solutions. But after we allow it to cool down, you will see a needle-like precipitates being formed again. We can say the same for lead bromide as well. Lead bromide, when heated with water, will form a colorless aqueous solution of lead 2 plus and bromide minus aqueous ions. And when you allow it to cool down, upon cooling, we will form needle-like white crystals. So lead bromide white precipitate will be formed upon cooling, and the precipitate will look like needles. Tiny needle-like crystals will be formed upon cooling. When it comes to lead iodide, however, lead iodide is yellow in color. When heated, it will form a colorless aqueous solution of lead ions and iodide ions. Lead ions and iodide ion solutions will be formed. Upon cooling, we will form small particles of golden precipitate. It might appear like glitter as well. So the golden yellow color precipitates will get reformed upon cooling our lead ions and iodide ion solution, which we prepared by heating our lead iodide precipitate in water. So some of the observations that we made are summarized here. To identify the presence of chloride, bromide and iodide ions, we can use a lead 2 plus ion solution. However, lead 2 plus ion solution will not be able to distinguish between chloride ion solutions and bromide ion solutions. This is because both lead bromide and lead chloride that is getting formed are white color precipitates. However, lead iodide is a yellow color precipitate. So as we add bromide ions and chloride ions with as we react bromide and chloride ions with lead 2 plus ions, these precipitates will be formed and they are going to be white in color. When you heat these precipitates with water, they will dissolve and will form colorless aqueous solutions. And after we allow them to cool down, they will form needle-like crystals. So the observation is dissolves in hot water and forms white needle-like crystals when we cool down the solution. So keep that in mind, students. When you heat a lead chloride or lead bromide precipitate with water, it will dissolve to form a clear solution or colorless solution. And after we allow this hot solution to cool down, it will reform a white color precipitate. When it comes to lead iodide, however, lead iodide was a yellow color precipitate. When you heat it with water, it will dissolve in hot water to form colorless solution and forms small solid particles of golden yellow precipitate when cooled. So when you cool down this hot solution, golden yellow color precipitate particles will be formed as the solution cools down. So these are the tests and the observations revolving around lead nitrate. To obtain these same observations, you can also use lead acetate as well. Identification of halides by chlorine water test. Sodium chloride, sodium bromide and sodium iodide aqueous solutions are taken into separate test tubes. Then add about 10 cubic centimeters of CCl4 carbon tetrachloride to it, and then add chlorine water and shake vigorously. So we take a test tube. We will first take sodium chloride solution into the test tube. We will add 10 cubic centimeters of carbon tetrachloride, and then we will add chlorine water. We will shake it very well, vigorously we will shake it, and then we observe if there has been any color change in the organic layer or carbon tetrachloride layer. So when you do this process or a few steps with the use of sodium chloride solution, we will not observe a color change. No changes occur when sodium chloride is used. The organic layer remains colorless. You will not observe a noticeable color change. So students, as we add carbon tetrachloride into our sodium chloride solution, sodium chloride is an aqueous solution, carbon tetrachloride is our organic layer. So this organic layer, since carbon tetrachloride has a higher density, will sink to the bottom, and the top layer would be our aqueous sodium chloride layer. So when we shake it, we usually try to mix whatever the dissolved ions or molecules in the aqueous layer with the organic layer as well. So adding chlorine and then mixing has not given us a very observable color change here. So we can see no reaction is taking place here. Then what happens if you take sodium bromide in our aqueous solution and then we repeat the same process with a sodium bromide solution? Meaning we take sodium bromide solution, we add 10 cubic centimeters of carbon tetrachloride, and then we add chlorine water to it. Then we shake the test tube really well. So then what happens? We are going to observe that the organic layer or the carbon tetrachloride layer is going to turn orange. Why is this happening? Chlorine molecules that enter the aqueous medium can displace the bromide ions that are present in the aqueous medium as bromine molecules. So chloride ions are formed while bromide ions are displaced as bromine molecules. So Cl2 turns into Cl1 minus and Br1 minus turns into Br2. So students, this indicates that chloride ions, this indicates that chlorine is going to oxidize bromide ions to form bromine. So chlorine acts as an oxidizing agent over here, and as you know, if you have studied the electrochemical series, you know chlorine or when it comes to the halogen group, the halogens in the upper parts of the halogen group are capable of displacing the ions of lower parts of the halogen group. So basically chloride molecules are capable of displacing bromide ions as bromine, while chlorine turns into chloride ions. So over here, that is what is happening, students. We can see chlorine molecules when they come into contact with bromide ions. So over here we have Cl2 coming into contact with bromide ions, and these bromide ions will turn into bromine. In the next slide you will see the same reaction, and Cl2 has turned into 2Cl1 minus. There are two sodium bromides, so that means two bromide ions are there. So bromide ions are going to be displaced with chlorine molecules. In the electrochemical series, you will observe that chlorine has a higher reduction potential, meaning chlorine prefers to be reduced more than bromine. That's why bromine molecules are formed when chlorine was added to a bromide ion solution. So in the presence of chlorine, bromide ions will get displaced as bromine molecules. So these bromine molecules, students, are non-polar molecule, and are they very soluble in aqueous mediums? Not very soluble in aqueous medium. However, in this setup, if you take this as a test tube, aqueous medium is present on the top layer where bromine is getting formed after the addition of chlorine water. So we have bromine molecules getting formed here, and these bromine molecules are now dispersed in the aqueous medium. They are not very soluble in water. However, the bottom layer is a non-polar organic layer. So when we shake this reaction mixture, the two layers will mix and the components in the two layers will also mix, allowing the bromine to enter the organic medium, because bromine is more soluble in a nonpolar organic solvent like carbon tetrachloride. So as bromine dissolves more and more in our carbon tetrachloride layer, the carbon tetrachloride layer will turn into an orange color. In the presence of bromine in the carbon tetrachloride layer, carbon tetrachloride will turn to an orange color medium. So that is what is happening here, students. So the color changes that I mentioned in the previous slide can be seen over here as well. But let's take a look at the slide from the top. So the ionic reaction that takes place when we add chlorine water to bromide ion solution is given here, right? Chlorine displaces bromide ions as bromine and chlorine turns into chloride ions. This displacement reaction shown above occurs because chlorine is more oxidizing than bromine. As I mentioned earlier, chlorine has a higher reduction potential. If you go through your electrochemical series, you will observe chlorine has a higher reduction potential than bromine. So when chlorine is added to a solution that contains bromide ions will get oxidized while chlorine gets reduced to form chloride ions. So bromide will get oxidized to form bromine. And then we would observe, since the solubility of bromine molecules in CCl4 layer is greater than in water, they easily dissolve in CCl4 layer and form an orange color organic layer. So bromine is a nonpolar molecule, CCl4 is a nonpolar solvent. So nonpolar molecules will dissolve in nonpolar solvents more. Water is a polar solvent. Bromine is not going to be dissolving in water that well. So bromine will dissolve very well in CCl4, carbon tetrachloride, and will make that carbon tetrachloride layer appear orange in color due to the presence of bromine in that carbon tetrachloride layer. So what we do over here in this particular reaction is summarized in this diagram. We have our carbon tetrachloride layer and bromide ion solution taken into the same test tube, right? You will see aqueous layer and organic layer very clearly separated when you are doing this experiment. And after adding chlorine water to the aqueous layer, we will start to quickly mix these two layers together. And after mixing it really well, as the layers separate again, you can very clearly see that there is an orange color associated with the organic layer or carbon tetrachloride layer, because bromine molecules that got formed in the aqueous layer dissolved more in the carbon tetrachloride layer, as bromine is more soluble in carbon tetrachloride or any other nonpolar organic solvent. So students, this is how we actually conduct this experiment to show the presence of bromide ions in an aqueous medium with the use of chlorine water and carbon tetrachloride. When it comes to iodide ion solutions, if you repeat the same process with iodide ion solutions, you will also observe a very interesting observation, which is once you add chlorine water to sodium iodide aqueous layer, the aqueous layer will start to get a little bit brown in color. As iodine gets displaced in the presence of chlorine, just like bromine got displaced in the presence of chlorine, in the presence of chlorine, iodide ions will get displaced as iodine. Iodine in the aqueous medium will be somewhat brown or orange brown color will be observed. and sodium chloride will be formed here as well. That is an aqueous solution. So, however, students, main observation would be the aqueous layer will little by little start to turn brown. But if you shake this mixture, now imagine in this setup also we have potassium iodide aqueous layer in the upper layer of the test tube, and the bottom layer in the test tube is basically our CCl4 layer. As we add chlorine water, the upper layer, the iodide ions will get displaced as iodine. And although iodine is not very soluble in water, the little iodine that dissolves in water turns the solution into a brown color. And when you mix the solution, the aqueous layer will not be very brown at that point, because iodine from the aqueous layer will go into the carbon tetrachloride layer, and the carbon tetrachloride layer at that point will appear purple. So students, when we do this same process for a potassium iodide solution, the observation would be that the organic layer will turn into a purple color. So ionic reaction is given over here, students. Before we move on to the observation, we can see iodide ions will get displaced by chlorine molecules into forming iodine, and chlorine will get reduced to form chloride. The displacement reaction shown above occurs when Cl is more oxidizing than iodine, and iodine molecules are more soluble in CCl4 than in water. Because of that, they easily dissolve in CCl4 and form a purple color organic layer. So as iodine enters the CCl4 layer will appear purple in color. So students, as I mentioned earlier, initially the iodide ion solution, or potassium iodide ion solutions, are colorless. They don't have a color. There's no brown color in a potassium iodide solution. Iodide ion solutions are colorless. But I wanted to indicate, as we add chlorine water, the iodide ions will turn into iodine before we shake the mixture. So if you allow it to react well before shaking, you will see as iodine gets formed in the aqueous medium starts to turn into a brown color. Then after we mix these two aqueous and the carbon tetrachloride layers, the aqueous layer will appear somewhat clear again, and the carbon tetrachloride layer is now dissolving most of the iodine in it. So therefore carbon tetrachloride layer will appear purple in color. So this observation is another good observation to make when you are doing the experiment. As iodine gets formed in the aqueous medium, you will observe that the aqueous medium is turning brown. So this is not necessarily over here originally, students. Over here is what we have over here is iodide, potassium iodide solution. Potassium iodide is colorless. What I have indicated here in brown is the I2 aqueous solution that gets formed after the addition of chlorine water to our potassium iodide solution. So this brown color is there to indicate before we mix the solution well after the addition of chlorine water, the top layer, the aqueous layer, will slightly start to turn into a brown color. But after you mix it, this brown color will mostly disappear, and since almost all of the iodine goes into the carbon tetrachloride layer, the carbon tetrachloride layer will appear purple in color. So observations and conclusions of the chlorine water test. When it comes to the observations, you have to notice the fact that when you are adding chlorine water to a chloride ion solution, do we get a color change? No. So when we add chlorine water to a solution like sodium chloride, what you have there is chloride ions. Can chloride ions get displaced by chlorine molecules? Not necessarily. They are basically not capable of reducing in the presence of chloride ions. Chlorine gas can't get reduced into chloride ions in the presence of chloride ions. They are part of the same equation. So therefore, there won't be any reaction. So if you carry out the chlorine water test and you see no color change at all, what does that mean? That means it could be that the halide sample that you are dealing with is chloride ions. It could be that the chloride sample or halide ion sample that you are dealing with is a chloride ion solution. So conclusion, bromide and iodide ions are definitely absent. If they were present, they are going to show either an orange color change or a purple color change. But Cl minus ions may or may not be present. We can't conclusively say chloride ions are present in the medium. If they very specifically have 3 separate test tubes telling one of these test tubes contain chloride, and then at that point when you do the chlorine water test, if that one test tube doesn't give you a color change, then you can say definitely that's a test tube with chloride ion solution. However, when you are carrying out a chlorine water test, if there is no color change, we can't say that this is due to only the presence of chloride ions in the medium. Chloride ions may or may not be present. It could be just water. At that point, would you get a color change when you add chlorine water to water? Nothing will happen. So chloride ions may or may not be present would be the correct conclusion. But we can very clearly say bromide or iodide ions are not there. When you do the chlorine water test, if the CC4 layer turns orange in color, then we can conclude that bromide ions are present in the medium. Without the bromide ions, bromine wouldn't be formed. Without bromine in the carbon tetrachloride layer, there won't be an orange color present. So bromide ions are present would be your conclusion if this chlorine water test that we outlined earlier results in forming an orange color organic layer. If a purple color organic layer is present, then at that point what can be your conclusion? That in the aqueous medium, iodide ions were present. Iodide ions were present would be your conclusion. Because for the organic layer to turn purple, you need to have iodine molecules in it. And for iodine molecules to get formed in the aqueous medium, you need to have iodide ions. So when chlorine water is added, iodide gets oxidized into iodine, and this iodine dissolves more in carbon tetrachloride layer or the organic layer, resulting in a purple color. So students, these are your conclusions based on these observations that are listed here. Now students, we are going to take a look at another test that can be used to identify the presence of iodide ions. So in this test, we are going to use CCl4, potassium iodide, and instead of adding chlorine water into potassium iodide solution, we are going to be adding bromine water over here. So we repeat the same process. We have carbon tetrachloride and potassium iodide solution, just like we took in the chlorine water test. But instead of adding chlorine water, we can add bromine water here. So when bromine water is added and then shaken vigorously, you will see that the carbon tetrachloride layer turns a purple color. So this test also can be used to identify the presence of iodide ions in the medium. Since bromine is more oxidizing than iodine, the iodine molecules formed by the above displacement reaction occur or dissolve more in the organic layer, causing the organic layer to turn purple. Potassium iodide, bromine will react together to form iodine that dissolves in water and form potassium bromide. So the iodine molecules that are getting formed over here are not very soluble in water. Although we know a small amount of iodine dissolves in water, it is not very soluble in water. So if you have a carbon tetrachloride layer in this mixture, when you mix this aqueous and carbon tetrachloride layer together, the iodine will get mixed or get released onto our organic nonpolar carbon tetrachloride layer. This will cause the CCl4 layer to turn into a purple color. So we have iodide ions reacting with bromine, and iodine and bromide ions will be formed. Iodine in the aqueous medium will appear somewhat brown, but once it dissolves in carbon tetrachloride layer, it will appear in a purple color. It will appear purple. So students, why is this happening? Why is chlorine able to displace bromide ions? Why is chlorine able to displace iodide ions? Why is bromine able to displace iodide ions as well? So let's take a look at that. Now, in the electrochemical series, you will see chlorine. Actually, fluorine will be above chlorine, but since we're talking about chlorine, bromine, and iodine, we'll take those three. Chlorine, bromine, and iodine are going to be found in this particular order. In the electrochemical series, we talk about reduction potentials. Chlorine is more capable of getting reduced than bromine. Let me first write the equations pertaining to these reduction potentials. So if you talk about reducing each of these, chlorine, bromine, and iodine, you will see chlorine prefers getting reduced more than bromine and iodine. So how do we determine that? The reduction potential of chlorine is going to be a larger positive value compared to the other two. So the reduction potentials, they decrease as we go down the electrochemical series from chlorine to iodine. So in this way, the reduction potentials will go down. Reduction potential decreases as we go down. Having a high reduction potential corresponds to the ability that these chlorine has to oxidize bromide ions and iodide ions. So having a high reduction potential means chlorine prefers very much to be reduced and stay in the form of chloride ions instead of chlorine. So if we introduce chlorine molecules into a solution that contains bromide ions, since chlorine is the one who prefers more to stay in the chloride or negative ion form, bromide ions will be oxidized to bromine, while chlorine gets reduced to form chloride. This is mainly due to chlorine having a larger reduction potential. Chlorine has a larger reduction potential compared to bromine and iodine. So chlorine has a more of an oxidizing power, or it is better oxidizing agent than the rest of bromine and iodine. So chlorine is capable of oxidizing bromide ions to form bromine. So students, then what about bromine? bromine, according to the trend that I just drew, bromine has a higher reduction potential than iodine, meaning in the presence of iodide ions, bromine is going to be capable of displacing iodide ions as iodine, because compared to bromine and iodine, bromine has a higher reduction potential. So if we introduce bromine into a solution of iodide ions will get displaced as iodine, as bromine prefers to stay reduced or prefers to get into the reduced form, which is bromide ion form, as bromine has a higher reduction potential than iodine. So students, this is the main reason why you would observe the previous observation we spoke about earlier, which is in the presence of bromine water, the iodide ions in the medium turned into iodine. This was mainly possible because why? Bromine has a higher reduction potential than iodine, meaning in the presence of iodide ions, if you introduce bromine water, iodide ions will get displaced by bromine into iodide, and bromine will turn into bromide ions. So students, this is something that you should keep in mind. After making notice of this particular theory part, we can now move on to the next slide. Now students, we have a diagram over here which we can color and develop a better idea about what type of color changes will be happening here. So we have the previous experimental setup present over here. We have an organic as a solvent layer and aqueous layer. So aqueous layer appears on top layer and organic layer will sink to the bottom, as in this case the organic layer is heavier than the aqueous layer. So CCl4 and aqueous potassium iodide layers are going to be colorless, students. CCl4 is colorless, and when it comes to potassium iodide also it should be colorless because iodide ions do not show a color in aqueous medium. When we add bromine into an aqueous iodide ion solution, bromine will get reduced to bromide ions and iodide ions in the medium will get oxidized to form iodine. So therefore, this area which is colorless, over here let's say this was originally colorless, so indicated in a little bit of a blue color. As we add bromine water, this colorless aqueous medium will gradually start turning brown. And after adding bromine, if you mix the two layers together, then this formed iodine will enter the carbon tetrachloride layer, which will result in producing a purple color in the carbon tetrachloride layer. So the entire CCl4 layer will be purple in color. Aqueous layer might appear a little brown because there might be certain amount of iodine molecules still dispersed in the aqueous medium, but majority of the iodine will dissolve in the carbon tetrachloride layer and turn that layer into a purple color. Aqueous layer might appear almost colorless, or there might be a hint of brown if certain iodine molecules are still remaining in the aqueous medium. If you have shaken this reaction mixture really well and extracted most of the iodine molecules into the carbon tetrachloride layer, then the aqueous layer will appear colorless. So students, this particular test also can be used to identify the presence of iodide ions. Now students, we move on to another test, which is identification of halides using concentrated sulfuric acid. If you take a little of each solid samples of sodium chloride, sodium bromide and potassium iodide into a few different test tubes, and then if you add concentrated sulfuric acid to those test tubes, you will see different observations. So using sulfuric acid, which is actually a strong oxidizing agent, we can observe these observations, and we can use sulfuric acid to identify the presence of chloride, bromide and iodide ions in the solid sample as well. So if you take sodium chloride and add concentrated sulfuric acid, you will see a white smoke, also known as a white fume, is formed. So in certain texts, it is also referred to as misty fumes. So when it comes to adding concentrated sulfuric acid to sodium chloride solid, the observation would be the formation of a white smoke or misty fumes, because HCl is formed. As soon as you add sulfuric to solid sodium chloride, you can see a white color smoke getting formed. That will be due to the formation of HCl gas. And sulfuric acid, now in this case the chloride ions were not oxidized, but sulfuric acid can oxidize the other ions that we are going to be talking about. For example, if you take a look at sodium bromide solid sample and add sulfuric acid to it, you will observe the bromide ions in sodium bromide get oxidized to bromine, and sulfuric acid, especially the sulfate anion, get reduced to form sulfur dioxide. So bromine gas will be formed, releasing sulfur dioxide as well. So bromine gas that is formed over here is a red-brown gas. Bromine gas is a red-brown color gas. So if you have a solid that is containing bromine or bromide ions in it, if you add sulfuric acid, concentrated sulfuric acid, you can see the formation of a red-brown color gas. This would indicate that the solid sample had bromide ions in it. If you do the same for sodium iodide or potassium iodide for that matter, if you take potassium iodide and carry out the same experiment, you would observe that in the presence of concentrated sulfuric acid, iodine gas will be produced. So iodine gas will appear purple, right? Even when you take a solid iodine piece and if you sublimate it, you can see the iodine gas being produced. What is the color of iodine gas? The color of iodine gas is purple. So a purple color gas will be produced when we add concentrated sulfuric to potassium iodide. So these are the balanced chemical equations for the reaction with concentrated sulfuric acid. We have sodium chloride reacting with sulfuric. Students, keep in mind, in this case the chloride ions are not oxidized. In this case the chloride ions are not oxidized. Over here sodium and chloride, or sodium 1 plus and chloride ions are present in sodium chloride solid. When we add concentrated sulfuric acid, what we have formed over here is hydrogen chloride, HCl. So oxidation number of Cl over here is still -1, and in sodium chloride, chloride is going to be present as a 1- ion. So oxidation number of the chloride ion will also be -1. When it comes to HCl, also the oxidation number is -1. There is no oxidation taking place here. Only thing that has happened is in the addition of sulfuric acid, HCl was produced as a gas. And this HCl produced, whenever HCl is produced as a gas, in any reaction you can observe that as a white color smoke, also known as a white color fume. Sodium bromide, when reacted with sulfuric acid, the bromide ions in the sodium bromide solid will get oxidized to form bromine molecules, and it will also form sulfur dioxide. As I mentioned earlier, sulfuric acid can act as an oxidizing agent, and as sulfuric acid oxidizes bromide ions to form bromine, sulfuric acid undergoes a reduction to form sulfur dioxide. So the oxidation number of sulfur over here is +6. However, you can see oxidation number of sulfur over here is +4. It has undergone a reduction. As sulfuric acid was oxidizing bromide ions into bromine, it has undergone a reduction to form sulfur dioxide. Apart from that, water and sodium sulfate will also be produced. Water and sodium sulfate will also be produced. When it comes to potassium iodide reacting with sulfuric acid, a similar reaction to the above reaction can be observed. Iodide ions will get oxidized. So iodide ions over here is -1 in oxidation number, iodine is 0. So -1 to 0 is a oxidation. Sulfuric acid has sulfur at the oxidation state +6, but sulfur dioxide, the oxidation number is +4. So from +6 to +4 is a reduction. So sulfuric acid reduces to form sulfur dioxide while oxidizing iodide ions to form iodine. And apart from these two products, water and potassium sulfate will also be produced. So students, these are the main reactions that you should remember when talking about sulfuric acid related identification tests for chloride, bromide and iodide ions. Now, this summarizes the findings that we discussed earlier. Concentrated sulfuric acid acts as an oxidizing agent and oxidizes bromide to bromine and iodide to iodine. So, not just a single bromide ion, 2 bromide ions will turn into bromine, releasing 2 electrons. And this is just a simplification of what happens over here. If you write the correct half equation, 2 bromide ions will turn into a bromine molecule, releasing 2 electrons, and 2 iodide ions will turn into iodine, releasing 2 electrons. Over here, we have not written the entire balanced ionic equation. We have not written it, so keep that in mind. And over here, you can see it reduces sulfuric into SO2. So sulfuric will turn into SO2. But since oxidizing capacity of sulfuric is not enough to convert Cl- into Cl2, Cl- ions are not oxidized here. So that is why we didn't see the formation of chlorine gas when we reacted sulfuric acid with sodium chloride. We saw the formation of a white color smoke or white color fume when we added sulfuric into sodium chloride. And I told you what they're forming over there is HCl, not chlorine. So it was only capable of forming HCl because sulfuric acid is not a strong enough oxidizing agent to oxidize chloride ions into forming chlorine gas. So therefore, students, you will not see the formation of chlorine gas. However, you will see the formation of HCl, which will give us an observation that we learned earlier, which is what is observation? A white color fume or smoke will be formed. So, and when a wet blue litmus paper is pointed at the HCl gas that is released, it will turn red. It is confirmed that the gas is an acidic gas. So, when white color fume is released, if you want to have a confirmation test, you can take a litmus paper, a blue color litmus paper that is moistened with water. If you hold it against the gas that is released, you will see the gas will turn this wet blue litmus paper into a red color. This would indicate that the gas is acidic. So students, what are the main observations over here? If you have these halides and if you react with concentrated sulfuric acid, you will observe the formation of a white color smoke when it comes to reacting concentrated sulfuric acid with chloride ions. With bromide ions, it will release a red-brown color gas, and with iodide ions, it will release a purple color gas. So I want you to remember these observations, very important when it comes to answering questions also at the exam. If you know this, it will make your life that much easier, because this test will give you clear, distinctive three different observations that can be used to separately identify solids containing chloride, bromide and iodide ions. So students, after looking at how concentrated sulfuric acid reacts with these halides, we can now move on to another acid. If you take concentrated nitric acid can also act as an oxidizing agent and help us to distinguish between bromide and iodide ions containing halides. So if you have concentrated nitric acid, HNO3, we can react this concentrated nitric acid with, let's say, a bromide ion or iodide ion. So when it comes to bromide ions, it will react with HNO3 to produce bromine gas along with nitrogen dioxide and water. Along with nitrogen dioxide and water. This is not the balanced chemical equation, students. So what I want you to see are the observations. If you take a look at bromine, bromine is a red-brown color gas. Bromine is a red-brown gas. So if we use red color, and when it comes to nitrogen dioxide also, it's going to be a brownish color gas. So you can observe when we add concentrated nitric acid to a bromide ion containing halide, you will observe a red-brown color gas being released. You will observe that it is releasing a red-brown color gas. So this also could be used to identify a bromide ion containing halide. If you add nitric acid, the result would be the release of a gas that is red-brown in color. If you add iodide, if you have iodide and if you add concentrated nitric acid to iodide, then what happens? So in the presence of concentrated nitric acid, iodide can turn into iodine. Now iodine is not red-brown, keep that in mind. Iodine is purple color, but as we saw in the previous instance, nitric acid reduces to form NO2, nitrogen dioxide, and water. So at this point, students, iodine, or let's talk about nitrogen dioxide first. This is red-brown, and iodine would be purple. So what you see is a mixture of these colors. You would not see a purple color gas being emitted or released. You will not see a red color or red-brown color gas being released. Instead, you will see a mix of these two, which is a bit of a darker gas or darker colored gas. So therefore, if we add concentrated nitric acid to an halide with an iodide ion in it, you will observe a darker colored gas being released. So two distinct observations. If a bromide ion was present, you will observe a red-brown color gas being released from this reaction. And if you have an iodide ion reacted with concentrated nitric acid, then you will not observe a red-brown gas being released. Instead, you will observe a darker colored gas being released. So students, this is an observation that can be used to separately identify halides that contain bromide ions and iodide ions. So nitric acid, concentrated nitric acid, can be used to identify halides that contain bromide ions and iodide ions separately. So with that, we can conclude our discussion here. The discussion that we were having over here is how concentrated acids can be used to identify halides with chloride, bromide and iodide ions. When it comes to sulfuric acid, if you had concentrated sulfuric acid, we saw HCl was formed in the presence of chloride ions. So that is, the observation would be white fumes. When it comes to bromide ions, we form a red-brown color gas due to formation of bromine. When it comes to iodide ions, due to formation of iodine, we will observe the formation of a purple color gas. So students, after this, after keeping these observations in mind, we can now move on to our next slide. In this slide, we are going to learn about how this chlorine water can be produced. So there are a few methods, two methods mentioned here. First method, addition of concentrated HCl to potassium permanganate, which is an oxidizing agent, will oxidize chloride ions to chlorine gas. So this chlorine gas that is formed can be sent through a sample of water, and we can dissolve the chlorine gas in water, and we can form an aqueous solution of chlorine to use for such an experiment like this one. So chlorine water can be produced by oxidizing chloride ions by reacting it with acidified potassium permanganate, or in this case we can directly use HCl without having to use a separate acid. If you use HCl, HCl contains chloride ions and the medium will already be acidified, and then to that medium if you add potassium permanganate, you have acidified potassium permanganate as well as chloride ions in the medium. So this is one of the reasons why we don't use HCl to acidify potassium permanganate. Now students, you have to keep that in mind. Whenever you are acidifying potassium permanganate for other reactions, not for this reaction, but when you are trying to acidify potassium permanganate for other reactions, for example, when you're trying to oxidize alcohols into carboxylic acids or aldehydes or ketones, you will use acidified potassium permanganate. Are we using HCl to acidified potassium permanganate? No. The reason is, if you use HCl to acidified potassium permanganate, the Cl minus in the medium will get oxidized to form chlorine gas. Instead, we use sulfuric acid. Sulfuric acid will not get oxidized, or sulfate anion will not get oxidized in the presence of acidified potassium permanganate. So therefore, sulfuric acid is the acid that we usually use when we are acidifying potassium permanganate. So an aqueous solution of chlorine can be prepared this way, and when we have chloride ions along with acidified potassium permanganate, chloride ions will get oxidized to form chlorine, and then we will have chlorine water. If you send this chlorine gas through a distilled water sample, you can actually form chlorine water. So the reaction related to that is given over here, students. Keep in mind, you need to remember these reactions. So 2KMnO4 reacts with 16 HCl to form 2 potassium chloride, 2 manganese chloride, 5 chlorine gas, and 8 water molecules. If you can write the half equations and then join them together, that will also be alright. However, if you can remember these, it will be easier. Chlorine water is formed this way. Chlorine gas dissolved in liquid water would result in chlorine aqueous or aqueous chlorine solution. And the second method is given here when it comes to producing chlorine water. The second method would be adding dilute HCl to sodium hypochlorite solution. We are interested in obtaining this hypochlorite ion. So in the presence of HCl, the hypochlorite ion can produce chlorine gas. Here the chlorine gas is formed and it dissolves in the water to form chlorine aqueous solution. Therefore, sodium hypochlorite solution is acidified with HCl to form chlorine water. The reaction for that is given here. When you react sodium hypochlorite with HCl, sodium chloride and chlorine will be produced, and this chlorine will dissolve in the medium to form chlorine aqueous solution, or otherwise known as chlorine water. So students, these are the theory parts that are revolving around this experiment 13, identification test for halides. So I hope by now you have learned about a few different tests that can be used to separately identify chloride, bromide and iodide ions in a solution. Now students, we have gone through all the theory parts revolving around experiment number 13, different identification tests for halide ions. By now, I hope you have gotten a good grasp on the different types of identification tests that are there to identify chloride, bromide and iodide ions. So now it is time for us to move on out of this classroom into the lab to actually conduct these experiments. I will meet you in the lab.
GCE Advanced Level Chemistry Practical number 13, Identification of Halide Ions. Aim of this practical is to develop skills of identifying chloride, bromide and iodide ions. In this practical, we will be using silver nitrate solutions to identify halide ions, lead nitrate or lead acetate to identify halide ions, chlorine water and carbon tetrachloride to identify halide ions, and finally we'll be using concentrated sulfuric acid to identify chlorides, bromides and iodide ions when they are separately present in solutions. So without further ado, let's move on to the reagents we need to carry this practical. To carry out this experiment, these are the reagents that you would need. We would be using sodium chloride solution, which is made out of sodium chloride solid. As you can see, it's a white color solid. We'll be using sodium bromide. Again, in front of it is the white color solid that we use to make this solution. We'll be using potassium iodide. Again, potassium iodide solid is in front of the solution, which is a white color solid. Apart from that, we'll be using dilute ammonia, concentrated ammonia, chlorine water. We'll be using carbon tetrachloride, CCl4. We'll be using dilute nitric acid, silver nitrate solution, a lead nitrate solution. So in the practical, we will be able to use lead acetate or lead nitrate solution. In this case, we have actually chosen to use lead nitrate. We'll be using concentrated sulfuric acid as well as a little bit of starch. Using this starch, we'll be making a starch solution later in the practical. Apart from that, apart from the reagents that we'll be using for this practical, we'll also be using some equipment such as test tubes and a wash bottle containing distilled water. Now, let's move on to the experiment. First, we'll be starting with how halide ions react with silver nitrate. Initially, we'll be taking sodium chloride, which will bring in chloride ions into the medium, and we'll be reacting it with silver nitrate, and we'll be observing the changes that take place. So let's take a little bit of sodium chloride solution and transfer it into a test tube. So in the sodium chloride solution, you will have sodium ions and chloride ions. We are testing for the chloride ions in this solution. After transferring small amount of sodium chloride, I will now add a little bit of silver nitrate. Now, silver nitrate will contain silver plus ions and nitrate ions. So, when silver ions come into contact with the chloride ions, we will see what happens. As you can see, when you react silver nitrate with sodium chloride, you'll be forming a white color precipitate. This entire solution now appears white as a result of formation of a fine precipitate that is silver chloride. If you let it stand for a while, you will see the precipitate sedimenting at the bottom, leaving the supernatant on the top. So this is silver chloride that is produced, which is white in color. So now we will take a portion of this silver chloride precipitate and transfer it into a different test tube. So I'll be transferring a little bit of this silver chloride suspension, I would say, into a different test tube. And then we will add a little bit of nitric acid and a little bit of dilute ammonia to see what kind of changes we can observe. So to the first test tube, I will do nothing. We'll keep it as our control to compare it with the results we get. To the second one, I'll be adding a little bit of dilute nitric acid. So to this silver chloride precipitate, I'll now be adding a little bit of dilute nitric acid. We'll give it a little swirl. As you can see, addition of nitric acid to silver chloride solid did nothing. It did not bring about any chemical change because silver chloride does not dissolve in nitric acid. Then we will take the remainder of the suspension, where we have silver chloride here, and we will add a little bit of dilute ammonia to see if dilute ammonia will be able to dissolve the silver chloride precipitate that we have here. As you can see, without even giving it a swirl, you can see the precipitate is starting to dissolve. Now let me give it a little shake. You can see the precipitate is starting to dissolve. Since we have a lot of precipitate, it takes a lot of ammonia or dilute ammonia to dissolve it, and it takes a little while. So we'll give it a little while until everything is dissolved. I'll have to add a little bit more dilute ammonia. Now you'll be able to see an almost clear solution because the dilute ammonia was able to dissolve the silver chloride solid that was present in this test tube. So with this, now you can see a nice comparison. where we started with mixing sodium chloride and silver nitrate, and we produced a precipitate, silver chloride. We'll add a little bit more water to see the precipitate a little bit more clearly. You can see at the bottom of this test tube, there is silver chloride solid formed. And then we took a little bit of that silver chloride precipitate and reacted it with nitric acid. We did not observe any change. That is because nitric acid does not dissolve silver chloride. And then later on, we took a little bit of silver chloride solid and reacted with dilute ammonia. Dilute ammonia, as well as concentrated ammonia, is capable of dissolving silver chloride solid. You can see a completely clear solution here because all of the silver chloride has been dissolved in the presence of dilute ammonia. So that are the reactions that we can do with chloride ions and silver nitrate. Now, let's move on to bromide ions. Let's take a look at how sodium bromide will react with silver nitrate. So, to introduce bromide ions, we have taken sodium bromide solution over here. So, we'll take a little bit of sodium bromide into a test tube, like so. And into this sodium bromide solution, we will add a little bit of silver nitrate. Silver nitrate solution will introduce silver ions into the medium. As you can see, as soon as I put a little bit of silver nitrate into the test tube, it will react with the bromide ions in the solution and will form a pale yellow precipitate. Now this is silver bromide. We'll mix it together quite well. You can see the precipitate that is formed over here is a pale yellow color. We'll compare the colors later on to silver chloride, silver bromide and silver iodide. But in this case, you can see the precipitate that is formed is going to be a pale yellow color. It is quite difficult to properly distinguish it from white color. But if you compare it against silver chloride, you will very clearly see that this is a pale yellow color. Right, so we will dilute this suspension of silver bromide a little bit further. After diluting it a little bit, now this is silver bromide solid particle suspended in aqueous solution. We'll be separating it into two other test tubes. Right. After separating it into two other test tubes, now we have three test tubes containing silver bromide. Now, to two of these test tubes, we will add dilute nitric acid to see can dissolve silver bromide, and we'll be adding concentrated ammonia to see if we can dissolve silver bromide. So, first of all, we'll take a little bit of dilute nitric acid, and we'll take silver bromide suspension, and we will add dilute nitric acid to see if there will be any observable change in the medium. As you can see, adding dilute nitric acid did not bring about any change. This is because dilute nitric acid is not capable of dissolving silver bromide solid. We would be moving on to adding a little bit of ammonia onto this. Dilute ammonia is actually not capable of dissolving silver bromide, so we'll be straight away adding concentrated ammonia to see if that is capable of dissolving the silver bromide suspension that we have over here. we have to take concentrated ammonia for this. So we'll take a little bit of concentrated ammonia solution. Upon addition of concentrated ammonia, you can see the solid starting to dissolve. Without even shaking it, the solid has started to dissolve. And now if I give it a little swirl, you will see all of the solid that was present over here is now dissolving in concentrated ammonia. So silver bromide is soluble in concentrated ammonia. We'll add a little bit more just to make sure that every particle here is completely dissolved. Right. So we'll leave it aside for a while and then we'll move on to the summary of what we learned here. When mixing bromide ions with silver ions, you will form a precipitate which is pale yellow in color, known as silver bromide, AgBr. It is pale yellow in color. We took a portion of that precipitate and reacted it with a little bit of dilute nitric acid, and we saw dilute nitric acid could not bring about any change as dilute nitric acid is not dissolving silver bromide. And then finally, we took a little bit of the silver bromide precipitate and reacted it with concentrated ammonia. In the presence of concentrated ammonia, silver bromide will dissolve to form a clear solution. Keep in mind, dilute ammonia is not capable of dissolving silver bromide. It is concentrated ammonia that is capable of dissolving silver bromide as it forms a complex with the silver ions. So that is it for bromide ions identification test with silver nitrate. Now let's see how iodide ions react with the silver nitrate solution. So to introduce iodide ions into the solution, we will be using potassium iodide. So we will take a little bit of potassium iodide solution into this test tube. And then we will add a little bit of silver nitrate to this test tube to see what changes take place. As you can see, upon addition of a little bit of silver nitrate into potassium iodide solution, we are starting to form a slight yellow color precipitate. This precipitate is silver iodide. So let me give it a little swirl. You can see a yellow color precipitate forming. Now this yellow color is quite low in intensity. You will not be directly identifying it as yellow if you do not compare it with a white background. So at the end of this practical, I will compare all of the three colors of silver chloride, silver bromide, and silver iodide separately, and I will show you the colors, how they compare against each other. But we have to know that silver iodide has a yellow, or sometimes it is described as a bright yellow precipitate. Now, as we did before, we will dilute this precipitate a little bit. Now it's suspended in water, right? So we'll take this solid suspension and transfer some of it into two other test tubes. After transferring it into two other test tubes, we will add a little bit of nitric acid into one of the test tubes to see if nitric acid is capable of dissolving the silver iodide precipitate that we have here. So let's add a little bit of nitric acid. As you can see, adding nitric acid into this precipitate did not bring about any change, as nitric acid cannot dissolve silver iodide that is formed. Then we will take another portion of the silver iodide precipitate we have and add a little bit of concentrated ammonia. So we will add a little bit of concentrated ammonia to see if it can dissolve this silver iodide precipitate that we have here. Now, in the previous two instances, as you added concentrated ammonia into silver bromide and as you added dilute ammonia into silver chloride, upon addition of these reagents, we saw an immediate change taking place. That is the dissolution of the solid. But once you add concentrated ammonia into silver iodide, you can see no change takes place. This is because concentrated ammonia and as well as dilute ammonia cannot dissolve the silver iodide precipitate that is formed. No longer how long you keep it aside for the reaction to take place, you will see that the reaction will not take place, as concentrated ammonia cannot dissolve silver iodide. So let's go through our observations one more time. As a summary, we initially took a little bit of potassium iodide solution, reacted it with silver nitrate and formed silver iodide precipitate, which is described as a bright yellow color precipitate. And then to a portion of it, we added a little bit of nitric acid. No change took place, as nitric acid cannot dissolve silver iodide precipitate. And finally, we added concentrated ammonia into silver iodide precipitate. Again, no change took place upon addition of concentrated ammonia into silver iodide. So these are the observations that you will get when you are doing a confirmation test or identification test for iodide ions with the use of silver nitrate. Now, let's compare the colors of the precipitates of silver chloride, silver bromide, and silver iodide. To do that, like we did before, we will be now adding silver nitrate onto sodium chloride, sodium bromide, and potassium iodide. So first of all, let's take a small test tube and take a little bit of sodium chloride. And to it, we'll add a little bit of silver nitrate. As we mentioned before, we'll be forming a white color precipitate, which is silver chloride. So the purpose of this section of the practical is to compare the colors of the three precipitates. So we will leave silver chloride precipitate here and we'll move on to reacting sodium bromide with silver nitrate. To this sodium bromide solution, let's add a little bit of silver nitrate. We can see a pale yellow precipitate forming. So once you compare it against the silver chloride precipitate, we can see the slight yellow color of sodium bromide reacting with silver nitrate, forming silver bromide. Right, so the silver bromide is slightly having a pale yellow color. So when you are comparing the two, you will be able to observe the two colors very clearly. Right. Now let's move on to silver iodide. So if you take potassium iodide and react it with silver nitrate, if you take potassium iodide and react it with silver nitrate, you will be forming a yellow color precipitate. This is referred to as a yellow color precipitate. Now this is a yellow color precipitate of silver iodide. As a result of reacting potassium iodide with silver nitrate, we obtained silver iodide, we obtained silver iodide precipitate, which is described as a yellow color precipitate. I know it's difficult to observe this yellow color, but when you compare it against a silver chloride precipitate, you will be able to notice the color difference. Silver chloride is a white color precipitate. Compared against it is silver iodide, yellow color precipitate. So now this thing precipitates, since it's very fine, it is suspended in water. It looks as if it's a cream or yellow color solution. No, it's a yellow color precipitate suspended in water. So this is a suspension of the precipitate. So now when you have all three compared against each other, you will be able to see the slight color variations of the three precipitates. Silver chloride being white and silver bromide having a pale yellow color in the precipitate, and silver iodide having a yellow color precipitate. All right, everyone. So that is going to be the comparison of the three precipitates formed when chloride ions, bromide ions, and iodide ions are reacted with silver nitrate. So I hope you can see the colors separately. And now let's move on to the next step in our practical. Let's take a look at how sodium chloride, sodium bromide, and potassium iodide will react with lead nitrate. Now, our practical book tells us that we have to use lead or lead acetate, but instead we'll be going along with lead nitrate, because the purpose of using either of those solutions is to introduce lead ions into the medium. So we'll be using lead nitrate, which is water-soluble ionic compound. So it will be bringing in lead ions into the medium without any problem. And each of these salts or salt solutions, sodium chloride, sodium bromide, and potassium iodide, will bring in chloride ions, bromide ions, and iodide ions into the medium when you are doing the experiment. So without further ado, now we have labeled our test tubes because it will be easier for us to identify what solutions are in them when we have already labeled them. So to an already labeled test tube, I will be taking in a little bit of sodium chloride solution. Let's take a little bit more. And now to this sodium chloride solution, or solution that contains chloride ions, I will be adding a little bit of lead nitrate. Now please observe, students, upon addition of lead nitrate, we are seeing a precipitate being formed slowly. So this precipitate is lead chloride, a white color solid. Water insoluble white color solid lead chloride will be formed, Pb Cl2 is the formula. So you can see a nice white color precipitate forming and already accumulating at the bottom. So we'll give it a little swirl and then leave it aside and move on to bromide ions. We will take another test tube labeled bromide ions and we will transfer some of the sodium bromide into this test tube. Now students, I have a little bit of sodium bromide solution over here. In this solution we have sodium ions and bromide ions. We are mainly carrying this test out for halides. So over here the bromide ions that we have are the main focus. So if you add a little bit of lead nitrate into this, you will see the bromide ions that is present in this solution will react with the lead nitrate, more precisely the lead ions in the lead nitrate solution, and will form again a white color precipitate. It was a quite fast reaction. As soon as you added lead nitrate, you could see the formation of lead bromide. Lead bromide PbBr2 is the formula and it is a white color precipitate. Both lead chloride and lead bromide happens to be white color precipitates. And now let's move on to potassium iodide. Let's move on to potassium iodide. We'll take a little bit of potassium iodide solution over here. Now, in the test tube over here, we have a little bit of potassium iodide solution which contains potassium ions and iodide ions. Our main focus here is the iodide ions. As we saw, iodide ions are added with lead nitrate. It will form lead iodide. Lead iodide is actually a very nice precipitate. A yellow color precipitate is formed instantly when you add lead nitrate into this. So let's give it a little shake. Now you can see the entire solution appears to be yellow. Do not be mistaken. This is not a yellow color solution that is formed. Instead, since the precipitate that is formed is quite fine in nature, it is dispersed in water, or we can say suspended in water, forming a suspension of the precipitate. So we will leave it aside to observe if it collects at the bottom. And now we actually have a small comparison that we can make. When you have chloride ions reacting with lead ions, we form lead chloride, which is a white color precipitate. When bromide ions react with lead ions, we formed lead bromide, again a white color precipitate. And when reacting iodide ions with lead ions, we form lead iodide, PbI2, which is a yellow color precipitate. Now, we want to see if these precipitates are soluble when we heat them after adding a little bit of water onto them. So let's separate some of these precipitates into a different test tube and let's try to dissolve them by heating them. Now let's start mixing these precipitates again and separating half of it to a different test tube, because we will be trying to dissolve these precipitates by heating them with water. So let's take the lead chloride precipitate, which is a white color precipitate, and let's mix it a little bit like so. And now let's transfer some of it to a different test tube. We'll do the same to lead bromide as well. Right? This is lead bromide. Let's mix lead bromide a little bit and transfer some of this lead bromide into another test tube. And finally, we'll do the same with lead iodide as well. We'll take a little bit of we'll take the lead iodide and mix it quite well and transfer some of the lead iodide suspension into a different test tube. Now that we have separated it into different test tubes, let's dilute them by adding a little bit of water. So to each of these test tubes, I'm going to be adding a little bit of water to dilute them further. I'm using a wash bottle to add a little bit of distilled water onto these 3 test tubes. Now students, you can see even after adding a little bit of water, the precipitates still prevail. Yeah, the precipitates still are there. They are still present as, this is lead chloride, a white color precipitate. Upon addition of a little bit of water, lead bromide is still present as a white color precipitate. And lead iodide is still present as a yellow color precipitate. Now, what we are going to do is, we will be adding all of these into a water bath. What you see over here is a water bath. You can see a spirit burner set up with a tripod and wire mesh and a beaker full of water. So we will be heating this water bath with the use of our spirit burner. So as the water heats up, we will be transferring these 3 test tubes onto our water bath. And we will observe over time how these precipitates will dissolve in the hot water. So we will give it a few minutes and we'll come back and see whether the precipitates have dissolved or not. Now students, please observe how some of the precipitate that we initially had has started to dissolve when we were heating this test tube up. Right? So when the test tube was heated, some of the precipitate started to dissolve in that hot water. So this was the lead chloride suspension we had, right, or lead chloride solid we had, has now started to dissolve. You have lead bromide solid, which is almost completely dissolved by now, right? So still some of it remains. You can see when I shake it, it kind of starts to dissolve a little bit better. And if you observe lead iodide solid, the solution has now started to kind of lose some of its color. That is due to most of the precipitate starting to dissolve. Now this color change is still not very clear, but if you leave it there for a little while longer, you will observe that all of the precipitate completely dissolves as you heat it up. So we'll give it a little bit more time, and once it's completely dissolved, we'll come back and observe the changes. Students, we are back after a while. Before we took a small break, what we did was we took a little bit of lead chloride, lead bromide, and lead iodide precipitates, and we transferred some of those precipitates into another set of test tubes, and then we added water onto those test tubes and we heated them for a while. Now we are going to be looking at the results. If you take the lead chloride precipitate has now completely dissolved in hot water. So for comparison, if I take lead chloride precipitate before heating it, you can see it was a white color precipitate. Now, after heating it with water, it has turned into a clear solution. So this is evidence that you can take lead chloride precipitate and dissolve it in hot water. Then we took a little bit of lead bromide, added a little bit of water, and we heated it for a while. So if you take a look at the results, you can see the lead bromide precipitate completely dissolved in hot water. And upon dissolving in hot water, it formed a clear solution. So this observation is evidence for the fact that lead bromide is soluble in hot water. And then we'll move on to lead iodide. Again, we took a little bit of lead iodide precipitate and we heated it with a little bit of water, and now you can see lead iodide precipitate completely dissolved in hot water and formed a clear solution. You do not see a yellow color in this hot solution because all of the lead iodide precipitate completely dissolved to form a clear lead iodide solution in hot water. So this is evidence that lead iodide precipitate can dissolve in hot water. So now, since we have shown that in hot water all the three halides of lead can actually dissolve, we will give it some time to cool down. We want to see, upon cooling down, whether these precipitates will be reformed. So we will wait for another few minutes and observe the formation of the precipitates of lead chloride, lead bromide, and lead iodide upon cooling these hot solutions. Students, you can see here when it comes to lead iodide hot solution, as it cools down, it starts to form lead iodide precipitate again. Earlier on, it was a clear lead iodide solution formed by dissolving the lead iodide in hot water. Now, when it is cooling down, you can very clearly see a yellow color lead iodide precipitate forming again. When it comes to lead bromide and lead chloride, it is somewhat slower in forming the precipitates, but as time passes by, those two will also form a white color precipitate. Now, we have allowed the solutions to cool down for 5 minutes. If you can see, there is a small precipitate starting to form when it comes to lead chloride. Right, lead chloride solution that was hot lead chloride solution is now starting to precipitate out solid lead chloride, which is white in color. So if I show you the precipitate that is being formed, I hope you can see needle-like white color precipitates being formed here. So if I let it stand for even a little bit longer, we can see the entire precipitate being formed and sedimenting at the bottom as a white color precipitate. So what you see here is upon cooling, the hot PbCl2 solution, which was a clear solution, when we cool it, we are forming PbCl2 solid, lead chloride, solid white color precipitate. And over here, we had clear solution of lead bromide, which was formed by heating lead bromide solid in hot water. And now we have allowed it to cool down for a while. So you can see when I mix it up, you can see again a white color precipitate that is being formed, which is lead bromide solid, PbBr2 solid. So upon cooling, lead bromide, hot solution, when you cool it, will be forming lead bromide solid. Over here, we have our lead iodide solution, which was a hot solution earlier on. Now it is cooling down. So as you can see, earlier on, this was a clear solution. When we heated lead iodide with some water, we saw that the yellow color lead iodide precipitate completely dissolved to form a clear solution. Now this clear solution has turned a little bit yellow again due to the formation of lead iodide precipitate. Now lead iodide has a glistening effect on it, right? If you are not sure whether the camera can capture it, the fine particles that are reforming upon cooling down, these fine lead iodide crystals has a small glistening effect which gives it like a gold dust color. But this is lead iodide solid being formed when you cool down the lead iodide solution that was formed with hot water. So those are the observations when you take lead chloride, lead bromide and lead iodide, and when you heat these precipitates, we saw all of those precipitates dissolved to form clear solutions, but upon cooling they reform the solid precipitates, lead chloride and lead bromide, which are white in color, and lead iodide, which is yellow, a bright yellow in color. So that is a summary of chloride ions, bromide ions and iodide ions reactions with lead ions. Now let's move on to the next step. Students, now let's talk about the chlorine water test for halides. In this test, we will be taking a look at how sodium chloride solution, sodium bromide solution and potassium iodide solutions react in the presence of chlorine water. As you know, these halide ions will react with chlorine water except for sodium chloride, sodium bromide and potassium iodide solutions. When they react with chlorine water, the halide ions will be displaced. For example, if you take sodium bromide, when sodium bromide reacts with chlorine water, Br minus ions will be displaced as bromine or Br2. If you take potassium iodide, the iodide ions in the potassium iodide solution will be displaced as I2 or iodine in the medium, right? So without further ado, let's move on to the chlorine test. In this test, we will be using carbon tetrachloride as the organic layer. So as you know, all of the bromine or Br2 and the I2 that is formed are non-polar. Non-polar substances are more soluble in nonpolar solvents. So that is why we are using carbon tetrachloride, our carbonic layer or organic layer. Let's take a test tube and transfer small amount of sodium chloride and we'll place it here. We'll take 3 test tubes and now we will transfer small amounts of each of the halide solutions first. This is the bromide ion solution. And we'll take the iodide ion solution as well. And now we have taken 3 test tubes, and onto those 3 test tubes we have taken the halide ion solutions. Now let's transfer small amounts of carbon tetrachloride CCl4, which is our organic solvent. Carbon tetrachloride, students, is a non-polar organic solvent which is denser than water. So what we have here is a sodium chloride solution. It's in aqueous medium. So when I add a little bit of carbon tetrachloride to this, I hope you can see this observation. The carbon tetrachloride sinks to the bottom. The reason for this is carbon tetrachloride or CCl4 is denser than water. So it will sink to the bottom, and at the same time you can see clear layer separation. It will be present as 2 layers. This is due to the fact that the organic layer over here, which is non-polar carbon tetrachloride, do not dissolve in the polar aqueous layer. So now we have a small amount of carbon tetrachloride at the bottom and aqueous sodium chloride at the top. And then we'll do the same to the other 2 test tubes as well. To the sodium bromide solution, I will be adding a little bit of carbon tetrachloride as well. You can see again a clear layer separation, as well as the fact that carbon tetrachloride sinks to the bottom because all of these are aqueous solutions. So when you add carbon tetrachloride to any aqueous solution, we expect it to sink to the bottom because carbon tetrachloride is denser than water. Now what I'm holding right now is our potassium iodide aqueous solution, and onto that I have added a little bit of the organic solvent, which is carbon tetrachloride. Now students, we will be starting from potassium iodide and we'll be moving on to sodium bromide and sodium chloride, and we will be adding a little bit of chlorine water starting from potassium iodide. So let's take potassium iodide with carbon tetrachloride over here, and let's add a little bit of chlorine water. So as you know, chlorine in the presence of iodide ions will displace iodide ions and turn iodide ions into iodine, I2. As you can see instantly, when I start adding chlorine water, you can very clearly see the formation of a brown color solution over here. This is due to chlorine water reacting with potassium iodide and forming I2 or iodine. Now, I2 is dissolved in the water layer. I haven't still mixed it up. And you can see, due to dissolving I2 in water, there's a slight brown color present. So if I shake it a little bit, you can now see the brown color is evenly spread in the water layer. Still, it has not gone into the carbon tetrachloride layer, which is the organic layer. However, currently iodine is dissolved in the aqueous layer. Iodine, or I2, is a nonpolar substance. And carbon tetrachloride at the bottom over here is also nonpolar. So as you know, likes dissolves likes, which means I2 should be dissolved more in the nonpolar carbon tetrachloride layer. So to do that, we have to first of all mix this mixture thoroughly. So let's do that now. Upon mixing it thoroughly, you can see that the organic solvent layer, which is the carbon tetrachloride layer, is turning purple. It has turned purple compared to how it was before. So this is due to iodine dissolving in the CCl4 layer. And if you keep shaking it for a while, and if you let it aside to stand for a while, you will see most of this color on the aqueous layer will decrease over time, and the intensity of the purple color on the carbon tetrachloride layer will increase. So the observation over here is the presence of a purple color in the CCl4 layer, which is evidence of the presence of I2 being formed upon addition of chlorine water. So this test is evidence that if you add chlorine water into iodide ion solution, if you add chlorine water into an iodide ion solution, the iodine or iodide ions will convert into iodine and will be displaced. And then if you add an organic layer like this, that iodine will dissolve in the organic layer due to its nonpolar nature, and you can observe the purple color like this. Now let's move on to sodium bromide solution. So we have sodium bromide solution. On the top layer over here is our aqueous sodium bromide layer, and at the bottom is our carbon tetrachloride layer. So to this, we are going to be adding a little bit of a chlorine water solution. So let's add a little bit of chlorine water. Now you can see, as soon as I add a little bit of chlorine water, the color of the top layer starts to change. This is due to the fact that when you add chlorine water, the bromide ions that is present in the medium gets displaced as bromine, or in other words, Br minus gets reduced to Br2. So Br2 in aqueous medium normally gives off a yellow-brown color, or in this case, it appears a little orange. So this orange color is present in the top layer. And then if you give it a little bit of a shake or swirl, you can see the color will go from the top layer to the bottom layer. Most of the color will transfer there, but the top layer will retain some color, but still we'll give it a shake and see. Now, after shaking it quite well, you can observe that the most of the color that was present on the top layer is no longer there. It has transferred onto the bottom layer. Bottom layer is our carbon tetrachloride. Carbon tetrachloride is nonpolar, as I mentioned before, and the bromine or Br2 that is formed is also nonpolar. So bromine dissolves in the nonpolar layer better than it dissolves in water. Water is a polar solvent. So bromine dissolves better in the nonpolar layer and turns that carbon tetrachloride nonpolar organic layer into an orange color. So the organic layer turning orange upon addition of chlorine water into a bromide ion solution and then shaking the solution well is evidence of bromine ions being present or bromide ions being present in the solution. So when you want to test for bromide ions, this is one test that can be done. And if the carbon tetrachloride layer, or instead of carbon tetrachloride, you can use chloroform as well. If the organic layer or non-polar organic layer turns an orange color, that is an indication of bromide ions being present in the aqueous layer. So as you can see, these are the observations when we add chlorine water into a bromide ion solution and then mixing it with carbon tetrachloride. Now, finally, we will be taking the sodium chloride aqueous solution that is coupled with carbon tetrachloride. So in this test tube, we have a layer of aqueous sodium chloride, which is clear, which is a clear solution. And we have at the bottom over here, carbon tetrachloride organic layer. Now we'll be adding a little bit of chlorine water onto the sodium chloride solution. Did you observe any changes? The answer to that would be no. The reason we will not see a change when we add chlorine water to a chloride ion solution is because chlorine will not, or Cl2 will not displace chloride ions because it's the ionic form of chlorine. So over here, you will not see any displacement or you will not see any color change happening just because we added a little bit of chlorine water. So when you do the chlorine water test to chloride ions, the observations would be no change upon addition of chlorine water to a chloride ion solution. So let's focus on the summary of this test. When we add chlorine water to a chloride ion solution, we observed no change. When we conducted the chlorine water test to a bromide ion solution, we saw that bromine was displaced, and when bromine gets dissolved in the organic layer or the nonpolar organic carbon tetrachloride layer, we can see that layer turning orange. This is an indication of the presence of bromine, Br2. And when we conducted the chlorine water test for iodide ion solution, we see upon addition of chlorine water, the aqueous layer turned brown, and then when we shake it well with the organic layer, which is the carbon tetrachloride layer, organic solvent layer, you will see the organic solvent will turn purple color. So this purple coloration indicates the formation of iodine, I2, and dissolving of iodine in the organic solvent layer will turn that solvent into a purple color. So these are the observations that are there when we conduct the chlorine water test. Let's move on to the test with concentrated sulfuric acid. Finally, we are moving on to the reactions that will take place when we react potassium iodide solid, sodium bromide solid, and sodium chloride solid with concentrated sulfuric acid. So now, first we'll take potassium iodide solid. Little bit of potassium iodide we'll take into a small boiling tube. And after taking small amount of potassium iodide solid into a boiling tube, let's add a little bit of concentrated sulfuric acid. As you can see, when we are adding concentrated sulfuric acid onto this potassium iodide solid, there was a purple color gas formed. And you can see that interior walls of this is also turning purple due to that gas being formed. So this is due to the release of iodine or I2 gas. So I2 gas is purple in color. When you react a good oxidizing agent like concentrated sulfuric acid with potassium iodide or iodide ions in the potassium iodide will be converted into I2 and form I2 gas, which is evolving here as a purple color gas. In the previous experiment we added concentrated sulfuric acid to potassium iodide solid, and we saw a purple color gas, which is iodine gas, I2 gas being formed. Normally, it is not advisable to have a lot of gases roaming around in a lab atmosphere. So we had to remove the sample that we did the experiment with in order to make sure the space that we do these experiments are kept safe. So in the future also, when we do the experiments for sodium bromide and sodium chloride, we will be removing those samples right after the practical is done, just to make sure the lab environment that we have here is kept safe. So let's move on to our second halide ion, which is sodium bromide. We'll take a little bit of the sodium bromide solid and we'll add it to a boiling tube like this. And now let's add a little bit of concentrated sulfuric acid to this sodium bromide solid. Let me take a little bit of concentrated sulfuric acid and add a little bit of that into the sodium bromide solid. You can see effervescence being formed, and it is orange in color. I'm not sure whether the camera can capture the fume being a little bit orange in color. You can see the interior walls of the boiling tube also is turning a little bit orange. This is due to the formation of bromine gas. In the presence of concentrated sulfuric acid, sodium bromide or the bromide ions in sodium bromide will be converted into bromine gas, which now is evolving as a orange color or red-brown color gas. Now we'll have to remove this sample from the lab. Finally, let's move on to sodium chloride. So concentrated sulfuric acid is a good oxidizing agent. Let's see what it does to sodium chloride. So let's take a boiling tube and add a little bit of sodium chloride onto that. It will be easier to add it like this at times. And before I add sulfuric acid, I would like to mention the reaction that is happening here. So once you add concentrated sulfuric acid onto sodium chloride, the chloride ions will not convert into chlorine gas. Instead, it will form HCl gas that appears as a misty fume. So the HCl gas can be tested with blue litmus paper, and at the same time we can use pH paper to identify how acidic this gas is. So here in this petri dish we have blue litmus paper as well as pH paper. To use them, we have to make sure that these litmus papers are wetted with a little bit of distilled water. The reason for us to add a little bit of water onto these papers before we expose them to the gas is to make sure that the gas will adhere to these papers and dissolve in the water that is present on the paper and can show us a color change by having those gases coming into contact with the paper properly. So now let's add some concentrated sulfuric acid onto our sodium chloride solid. Now, as I mentioned earlier, upon addition of sodium chloride, you will see a gas evolving. Now, this gas is going to be a white color gas, or we call it a misty fume. You wouldn't necessarily have a characteristic color to it, so you cannot identify chloride ions by just adding sulfuric acid. But we can identify the gas that is evolving with the help of litmus paper. As you can see, when I hold a wet litmus paper onto this gas, the wet blue litmus paper is turning red. This is an indication of the gas being acidic. Now let's try using a pH paper to determine the acidity of the gas. Immediately, when you hold the pH paper, you can see the pH paper is turning red. Red indicates high acidity. However, after a while, we will compare it against the pH scale that is provided with the pH paper book. Right, everyone? Like I mentioned, upon addition of sulfuric acid to sodium chloride, we produced HCl gas, and we confirmed it with the use of litmus paper. Blue litmus paper turned red, and pH paper turned also into a red color. So now if you compare pH paper guide that is given over here, it's a bright red color, which indicates the pH of the gas that is released is between 1 and 3. So this is a highly acidic gas that is produced. If I show it to you over here, acidic gas that is produced, which indicates it is HCl that was released when concentrated sulfuric acid was added onto a sodium chloride solid. That brings us to the end of this practical 13. In the last section of the practical, we looked at how sodium chloride, sodium bromide, and potassium iodide reacts with concentrated sulfuric acid. To summarize, potassium iodide, when added with concentrated sulfuric acid, we saw the evolution of a purple color gas, which is I2. And then when we added concentrated sulfuric acid to sodium bromide, we saw that orange color effervescence being formed, indicating the presence of bromine gas, or the formation of bromine gas, which is an orange color gas. Finally, when we added concentrated sulfuric acid to sodium chloride, we saw that a white color gas was formed, or we call it misty fumes, that is acidic in nature. We tested its acidity with pH paper as well as blue litmus paper. So we confirmed the gas that is produced is acidic. So the gas that was produced upon addition of concentrated sulfuric acid was HCl. We cannot identify sodium chloride by adding concentrated sulfuric acid, as the gas that is evolved is going to be colorless. But the other two halides, bromide ions and iodide ions, can be identified by the color of the gas that is evolved. If a purple color gas evolves, that solution would have contained iodide ions. If a brown color or maybe orange color gas is evolved, that indicates the presence of iodide ions. So that will be all for this practical. We will be moving on to the important theory parts and questions related to this practical in our next session.
Students, here we are going to be discussing some questions revolving around experiment number 13. In the beginning of this experiment, we discussed the theory parts revolving around this experiment number 13, and then we moved on to the lab, actually conducted the experiment, and now we will be taking a look at some past paper questions, and we'll learn how to answer these questions in this session. Let's take a look at this first question we have over here. An aqueous solution contains chloride, bromide, and iodide ions. All three ions, or three halide ions that we spoke about in this particular practical is mentioned here. Now they're asking how the presence of these ions can be confirmed experimentally. So state how the presence of each of these ions can be confirmed experimentally. So I hope you remember when it comes to our experiment that we did, or the theory parts of the experiment, we learned a few different tests. Let's go over them very briefly here. We learned about adding silver nitrate to these solutions containing these ions, and silver chloride, silver bromide, and silver iodide was formed. Silver chloride was white, silver bromide was a very pale yellow color, and silver iodide was a slight yellowish precipitate. And then we learned that they are not reacting with acids. They do not dissolve in dilute nitric acid. And then we learned when you are trying to dissolve them in aqueous dilute ammonia, only silver chloride will dissolve. Silver bromide and silver iodide does not dissolve in aqueous dilute ammonia. But if you take concentrated ammonia, silver bromide will dissolve, but not silver iodide. Silver iodide does not dissolve in even concentrated ammonia solutions. And after learning about that, we moved on to lead nitrate. So if you add lead nitrate or lead acetate to chloride, bromide, or iodide ions, it forms three different precipitates. Lead chloride, lead bromide, and lead iodide are the precipitates. Lead chloride and lead bromide were white color precipitates, so you can't use lead 2+ ions to distinguish between chloride ions and bromide ions. because lead chloride and lead bromide are white color precipitates. However, lead iodide was a yellow color precipitate. And we saw lead halide precipitates that we just spoke of, lead bromide, lead chloride, lead iodide, they will dissolve in hot water. And then if you allow the solutions to cool down, they will reform their precipitates. Afterwards, we also moved on to chlorine water test. We saw chlorine was capable of displacing both bromine and iodine from bromide and a iodide ion solution. So that was our chlorine water test, and later on we observed how concentrated sulfuric acid can oxidize bromide and iodide ions to form bromine and iodine. Can we oxidize chloride ions with the use of sulfuric acid? No. Instead, when we add concentrated sulfuric acid to a chloride ion, a halide containing chloride ion, you would observe the formation of a white fume or white smoke. This is due to the presence of formation of HCl gas. When it comes to nitric acid, if you use concentrated nitric acid, we can identify the presence of bromide or iodide ions in a halide. So these are the main parts we looked at in our theory part of this experiment, and then we observed these observations in the lab as well. So we have a few tests at hand that we can use. One of the simplest and the easiest types of tests you can use is addition of silver nitrate. So you can take this solution, the solution that we have over here, right? So imagine you have to write it, you have to write the answer as a statement, but let's observe what is happening over here. We have a solution that contains all three: chloride ions, bromide ions, and iodide ions. So if you add dilute nitric acid, right, followed by silver nitrate aqueous solution, you will see the formation of a precipitate. So if we take a small sample of the solution, so this is not the entire solution over here. Imagine we have taken a small sample of the solution that contains chloride, bromide, and iodide ions. And when we add our silver nitrate, you will form a precipitate here. So let's say this is the precipitate. And the precipitate is going to be not entirely white, because if bromide and iodide ions are present, the silver bromide and silver iodide precipitates are not exactly white, right? There will be a yellowish tint or small hint of yellow color in the precipitate over here. So we can say yellowish precipitate, not a yellow precipitate, but yellowish white precipitate will be formed, right? Based on which ion is present there more, it would either be more white or a little bit more towards yellow, based on whether iodide ions are present in the medium more or chloride ions are present in the medium more. So this precipitate is basically the mix of silver bromide or silver chloride, let's start with that, silver chloride, silver bromide, and silver iodide. All three together, we have this precipitate. So how do we show the presence of silver chloride, silver bromide, and silver iodide separately? How do we do that? We can take this precipitate, we can filter it out, and we can take the precipitate separately. Imagine that this is just the precipitate. To this, if you add dilute ammonia solution, if now after adding, we'll have a water level here, so it's an aqueous solution. So certain amount of the precipitate will dissolve. Once you add dilute ammonia, certain amount of the precipitate will dissolve. This will indicate that silver chloride was present in the precipitate, because in dilute ammonia only silver chloride will dissolve. All the other silver bromide and silver iodide precipitates do not dissolve in dilute ammonia. I hope you remember the equation. So we learned the equation. If you have silver chloride solid, and when you react ammonia with it, NH3, you would get AgNH3 twice 1 plus, this is an aqueous complex along with chloride ions. So students, this is how silver chloride solid will dissolve in dilute ammonia, forming this silver ammonia complex. And due to this reaction, when we add a small amount of, let's say when you add a volume of dilute ammonia, a small amount of silver chloride that is present in the precipitate mix will dissolve, and you can see the precipitate is decreasing. So the observation would be a portion of the precipitate dissolves when dilute ammonia is added. So the first step would be to add dilute nitric acid, and followed by the addition of silver nitrate. Upon addition of silver nitrate, a yellowish white precipitate was formed, and then we can separate the precipitate. And if you add dilute ammonia to the precipitate, a portion of the precipitate will dissolve. This will indicate that silver chloride was formed and was present in the precipitate. So this confirms the presence of chloride ions in the initial solution. And then if you again take the remainder of the precipitate and react it with concentrated ammonia, if you add concentrated ammonia to this, you will observe that another portion of the precipitate will dissolve, leaving behind only a small yellowish precipitate. So why did another portion of this precipitate dissolve? Another portion of the precipitate dissolved because right now all the silver chloride was removed, and now we only have silver bromide and silver iodide in the precipitate, and silver bromide will dissolve in concentrated ammonia. So therefore students, upon addition of concentrated ammonia, silver bromide will dissolve and come into the medium. Silver bromide will also form the same silver ammonia complex, and instead of writing this equation, if you substitute the silver chloride with silver bromide, you will get the same equation, except for the fact that the released ion is not going to be chlorine. It's going to be a bromide ion, not a chloride ion, but a bromide ion. So the second step after the removal of silver chloride from the medium was to add concentrated ammonia, and after adding concentrated ammonia, another portion of the precipitate will dissolve, indicating silver bromide was present in the precipitate. Silver bromide was there due to bromide ions being present in the initial solution. So this confirms the presence of bromide ions in the initial solution. And what about the remainder of the precipitate? So the remainder of the precipitate indicates the fact that there was a precipitate that was not soluble in concentrated ammonia also. So, and this precipitate is a yellow precipitate. So this is another indication. What we have left here is silver iodide. However, students, if you want to have a confirmation test, you can remove or filter this silver iodide precipitate, you can wash it and dry it, and then you can add concentrated sulfuric acid. So in the presence of concentrated sulfuric acid, it should release a purple color gas. In the presence of concentrated sulfuric acid, it should release a purple color gas. So this is going to indicate the fact that the final precipitate, portion of the precipitate that did not dissolve, was in fact silver iodide. The purple color gas that was released was iodine. That means the precipitate was silver iodide, and silver iodide precipitate was formed due to the initial solution having iodide ions. So this is the answer to this question. So when you are structuring the answer, you have to write these few main statements. You have to write that if you take a small portion of the initial solution, and then if you add dilute nitric acid followed by silver nitrate, you will see a white yellowish precipitate is going to be formed. And if you take that precipitate and if you add dilute ammonia to it, you will see a portion of the precipitate dissolves. This indicates that you have had silver chloride in the precipitate, because in dilute ammonia only silver chloride dissolves. And then if you take the remainder of the precipitate and add concentrated ammonia to it, you will observe another portion of that remaining part of the precipitate will dissolve. This indicates that silver bromide precipitate was present, as silver bromide will dissolve in concentrated ammonia. And then the undissolved part, even in concentrated ammonia, would be our silver iodide. And if you remove the silver iodide precipitate and react it with concentrated sulfuric acid, you will see the evolution of a purple color gas, and this will be confirmation that initial solution had iodide ions in its medium. So that is the answer to our first question. I hope you were able to make note of how to structure the answer, as I explained how to write the answer in the last part. So this question should be handled in that particular way. Now let's move on to the next question. So now we are at the second question. If you are provided with a solution of copper bromide, CuBr2, explain or state the chemical tests to confirm the presence of Cu2 plus and Br1 minus ions in the solution. So we have to mention the chemical tests that are going to be used to confirm the presence of Cu2 plus and Br1 minus ions in the medium. So this is quite easy, students. So one of the first things that you can do to show the presence of Br1 minus is basically taking this solution. We have a solution, we can take a small sample of the solution, and if you add carbon tetrachloride, CCl4, to this solution, now we have our CuBr2 solution here. If you add chlorine water to this, Cl2 water, chlorine water, what would happen? The bromide ions in the medium will get oxidized to form bromine. And after adding chlorine water, we will mix these two layers really well. We'll shake it really well and mix it really well. And at that point, now before we mix it really well, both of these layers will be colorless. But after we mix it, students, we will observe that the CCl4 layer will be orange. Br2 will be there. So therefore, you will observe there's a CCl4 layer as an orange color layer. Br2 will dissolve more in CCl4. So therefore, when Br2 dissolves in an organic layer, it will appear orange in color. And over here, we have the aqueous layer. In the aqueous layer now, what you mainly have is chloride ions. Now, chlorine water that we added, it got reduced to form chloride ion while oxidizing bromide ions in the medium into bromine. And once we shake the two layers together or mix the two layers together, the bromine that was formed in the aqueous medium will dissolve more in CCl4 layer, as bromine prefers to be dissolved more in CCl4 layer. As bromine is nonpolar, CCl4 is nonpolar, it will not be very soluble in a polar solvent like water. So bromine will move to CCl4. And when bromine is present in CCl4, the CCl4 layer or the organic layer will appear orange. So that is one way that you can observe or prove that bromine or bromide ions was present in CuBr2 solution. There are other ways also. If you take silver nitrate, if you add a little bit of silver nitrate into this medium, aqueous medium, the bromide ions and silver ions will get together and form our pale yellow color silver bromide precipitate. And you can separate this precipitate and try to dissolve it in dilute ammonia. You can write the formed precipitate does not dissolve in dilute ammonia, but the formed precipitate will dissolve in concentrated ammonia. This also indicates the fact that we have had bromide ions in the initial solution, because once we add silver ions into the medium, silver bromide would be formed, and silver bromide is not a precipitate that will dissolve in dilute ammonia solution. However, it will dissolve in concentrated ammonia solution. Can it be silver iodide? No, silver iodide is not going to be soluble in a dilute or concentrated ammonia. So therefore, definitely not silver iodide. Is it silver chloride? If it was silver chloride, when we initially added dilute ammonia, it should have dissolved. It didn't dissolve in dilute ammonia. So therefore, this is definitely silver bromide if it only dissolves in concentrated ammonia. So that's another way of identifying the presence of bromide ions in the medium. And then we have, students, over here the identification for copper. So bromide ions can be identified in the two ways that I mentioned. But what about copper? Copper 2 plus. So copper 2 plus, students, if you take copper 2 plus and react it with dilute ammonia, it will form copper hydroxide. It will form copper hydroxide. It will form copper hydroxide. This is a pale blue color precipitate. This is a pale blue color precipitate. If you take this pale blue color precipitate, which is copper hydroxide, and add concentrated ammonia to it, or we can also say excess ammonia to it, then you will form a copper ammonia complex which is dark blue in color. So this aqueous solution or the complex that is formed is dark blue in color. So this is a confirmation test that can be done to identify the presence of copper 2 plus ions in the medium. This is one way that we can identify the presence of copper 2 plus. Now let's move on to another way that we can identify copper 2 plus in the medium. If you take copper 2 plus ions and react it with potassium ferrocyanide K4 FeCN6. If you react copper 2 plus ions with potassium ferrocyanide, then you would see the formation of a chocolate brown color precipitate. So copper FeCO2 FeCN6. Copper ferrocyanide is a brown color, often referred to as chocolate brown. Brown precipitate will be formed. So students, this is how we can identify copper in another way. First method that we explained was addition of ammonia. Dilute ammonia will produce copper hydroxide, but if you add excess ammonia or concentrated ammonia to copper 2 plus ion solution, after adding dilute ammonia, the copper hydroxide precipitate, pale blue color precipitate, will dissolve in concentrated ammonia. It will form a dark blue color solution. Basically, one copper 2 plus ion will form 4 coordinate bonds with 4 ammonia ligands and will form a complex ion that is going to be water soluble. So therefore, the precipitate CuOH twice will dissolve in excess ammonia or concentrated ammonia to form a dark blue color solution. This is going to be our confirmation test for the presence of copper 2 plus ions in the medium. Or else you can use this test as well, where you use potassium ferrocyanide solution and add the potassium ferrocyanide solution into Cu2 plus aqueous solution. You will see a brown color precipitate getting formed, which is copper ferrocyanide. So copper ferrocyanide is a brown color precipitate. This can be used as a confirmation test as well. So now we have learned the two main methods that we can use to identify copper 2 plus ions, and earlier we learned how to identify bromide ions in this copper or CuBr2 solution. So let's move on to the next question. Now we move on to the third question. Explain whether concentrated nitric can be used to distinguish between potassium bromide and potassium iodide. So can we use nitric acid to distinguish between potassium bromide and potassium iodide? Yes. I think one of the last things we learned when it comes to our theory part was we discussed, apart from using concentrated sulfuric acid to identify different halides, we can also use concentrated nitric acid. So when it comes to sulfuric acid, we saw when we react concentrated sulfuric acid with sodium chloride, a white color fume or smoke was produced due to the production of HCl gas. And when we add sulfuric acid to a sodium bromide, and when we add concentrated sulfuric acid to sodium bromide, we saw the formation of a red-brown color gas due to the formation of bromine gas. And finally, when we added concentrated sulfuric acid to potassium iodide, we observed the formation of a purple color gas due to the formation of iodine gas. So students, these were the observations with concentrated sulfuric acid. With concentrated nitric acid, we discussed what will take place, but we will refer to them here as well. So yes, the answer would be yes, we can use nitric acid to distinguish between KBr and Ki. So if you take KBr and react it with nitric acid, HNO3, the bromide ions turn into bromine gas, Br2, and the nitrate ions turn into nitrogen dioxide. So this will mainly be what This will mainly be the products that are getting formed. And when it comes to bromine gas would be a red brown color gas, and so will nitrogen dioxide be. So nitrogen dioxide and bromine gas, both of them are going to appear red brown, both of them. So when we add nitric acid to potassium bromide, not just any nitric acid, concentrated nitric acid should be added. So concentrated nitric acid is a oxidizing agent, good oxidizing agent. So if you add concentrated nitric acid to potassium bromide, you will observe bromine gas and nitrogen dioxide being formed. Both of these gases are red-brown in color. So you will observe the emission of a red-brown color gas from the reaction mixture. This will be used to identify potassium bromide. What will happen if you react potassium iodide with, now the question was, how can we use concentrated nitric acid to separately identify potassium iodide and potassium bromide, right? So if you add potassium iodide and concentrated nitric acid together, you'll be forming iodine gas along with nitrogen dioxide and water. So iodine gas is, like I mentioned in the theory parts, a purple color gas. Iodine is a purple color gas. Iodine will be produced as a gas here, and iodine gas will be a purple color gas. And we already know what is the color of nitrogen dioxide. Nitrogen dioxide is red brown. So when you mix purple and red brown together, would you observe a red brown color gas, or would you observe a darker colored gas? So the color of this gas, this is definitely a colored gas, but the color would be a darker color. So the observation that will be noticed when you add nitric acid with potassium iodide would be a darker colored gas is emitted, and we can use that observation to separately identify potassium iodide from potassium bromide, because if you add concentrated nitric acid to potassium bromide, a red brown color gas will be produced. Only that observation will be there, but over here a darker colored gas will be produced, not a red brown gas, because when both iodine and nitrogen dioxide are produced together, it will be a mixture of those two gases that we can observe. So you can't observe a single red-brown color gas being formed. Instead, it's a mixture of the two gases. It's a darker colored gas that you're going to be observing here, right? So you won't observe just purple or just red. It's a mix of the two, which is going to be a darker color. So yes, when it comes to your answer, you would have to write that over here. Yes, we can use concentrated nitric acid to distinguish between these two halides. When you're adding nitric acid to KBr, concentrated nitric acid will oxidize bromide ions to form bromine, releasing a red-brown gas, and nitric acid will reduce onto forming nitrogen dioxide, which is going to be also a red-brown color gas. So when you add concentrated nitric to potassium bromide, the observation is red-brown color gas. But when you add potassium iodide with concentrated nitric acid, observation is not going to be the evolution of a red-brown color gas. It is not that observation you're going to observe. You're going to observe the release of a darker colored gas, because this is the reaction that happens, releasing iodine and nitrogen dioxide together. So you have to mention that in your answer. Let's move on to the next question. Which of the following can be used to distinguish between potassium bromide and potassium iodide? We have potassium bromide and potassium iodide again. So answer for this question is quite easy, since we have discussed the addition of concentrated nitric acid in the previous question as well. Can we use HCl for this? Can we use HCl for this? No, we can't use any of the other substances that are given here. Only possible answer is nitric acid. So the answer to this question is HNO3. HCl, sodium hydroxide, ammonia, or even acetic acid or ethanoic acid. None of them can separately identify potassium iodide and potassium bromide. So if you have nitric acid, as explained in the previous question, you can identify potassium bromide and potassium iodide from one another. So now we move on to the fifth question. So this question is found towards the latter parts of a MCQ paper, where you have two different statements, and we ask whether the first statement is true or false, and whether the second statement explains the first statement, or if it doesn't explain the first statement, or whether the second statement is false or just true. So let's take a look at the answer here. Although silver chloride is soluble in aqueous ammonia, Ag2O is not. Is this statement true? Yes, we know silver chloride is soluble in aqueous ammonia. Actually, it is soluble in dilute ammonia also. But is it true that silver oxide doesn't dissolve in ammonia? The answer is no. Silver oxide does dissolve in ammonia, and we in fact use this reaction when preparing our tolerance reagents. So if you take silver 1 plus ion solution, or if you take, let's say, silver nitrate and react it with an base, you will observe the formation of Ag2O, silver oxide. Now you must be asking, how is that going to happen? Won't it form silver hydroxide? Silver hydroxide, you can argue that the silver hydroxide is getting formed and it is unstable, students. So two silver hydroxides react to form silver oxide. So what happens here is, when you react silver 1 plus ions with a base like sodium hydroxide, you will observe the formation of silver oxide, not silver hydroxide. Silver hydroxide will momentarily be formed and quickly it will dissociate into forming silver oxide and water. So silver hydroxide is not stable. So as you add a sodium hydroxide solution into silver 1 plus ion solution, you will first quickly form silver hydroxide, but you will not observe the formation of silver hydroxide because this is unstable. It will quickly break down to form silver oxide. Silver oxide is more stable and silver hydroxide is not stable. So as soon as you add hydroxide ions, the main product that you're going to observe is silver oxide. And silver oxide, students, silver oxide will dissolve in ammonia. If you add ammonia, it will dissolve to form this silver ammonia complex. So this complex is known as ammoniacal silver nitrate complex. When you are preparing this to prepare our tolerance reagent, you will form this, and alongside it you will have nitrate ions as well, nitrate ions from silver nitrate solution. So this is your ammoniacal silver nitrate solution. When you're forming tolerance reagent. How do you form the tolerance reagent? We will take silver 1 plus aqueous ion solution and we will add a few drops or small amount of sodium hydroxide. So at that point, silver hydroxide, which is very unstable, will be formed, and silver hydroxide immediately will turn into silver oxide, and silver oxide Ag2O is now present in the medium as a precipitate. And then what are we going to do to it? We will be adding to the same medium, we will be adding ammonia. So in the presence of ammonia, you will observe that this silver oxide dissolves to form this silver ammonia complex, and along with the nitrate ions in the medium, we can say that this particular complex will be formed, and this is what is known as ammoniacal silver nitrate. Since silver oxide is soluble in ammonia, definitely the first statement where it states that silver oxide is not soluble in ammonia is false. So this is a false statement. What about the next one? Oxygen is more electronegative than chlorine. Is it a true statement? Yes, oxygen is more electronegative than chlorine. We know the electronegativities. We usually learn fluorine is quite electronegative, then oxygen, and then nitrogen. So when it comes to oxygen, definitely it is more electronegative than chlorine. If you remember the electronegativities across the period, you would remember we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Fluorine is basically the most electronegative element, that is 4.0, and you can remember as you move to the left, electronegativity decreases by 0.5 when it comes to the second period. So oxygen is 3.5, nitrogen is 3.0, carbon is 2.5, boron is 2.0, this is 1.5 and 1.0. And chlorine here is considered to be having an electronegativity of 3.0. So if you compare oxygen and chlorine, yes, very clearly oxygen is more electronegative than chlorine. So it is true. But is it explaining this false statement? Anyway, this statement is false, so therefore only two answers can be there. So since the statement is false, we don't have to worry about whether it is explaining the first statement or not. So there are two false statements or false responses over here for the first statement. So out of these two, we are going to go with the answer 4, because the second statement is a true statement. So the answer is false and true only. So therefore, the answer would be 4 in this case. Then we move on to the sixth question. What can be used to distinguish between KBr and HI? So we need to learn which of these given substances actually can be used to separately identify these two halides, KBr and HI. Can we use HBe, HI, all of these things are not going to be used. For example, you can't use HBe or HI. Can we use iodine dissolved in chloroform? No, iodine is already in the oxidized form of iodide ion. So therefore, you can't use iodine. That is not also an answer. We have a bromine dissolved in toluene. So over here, students, we have two main compounds. We have HBr and HI. So let's say we are mainly talking about bromide and iodide ions, let's say. So if you have bromide and iodide, we use a different color for this. We have bromide ions and iodide ions. What will happen if you add bromine water? What will happen if you add bromine water to a solution containing bromide ions? Let's see. So we learned we can identify the presence of bromide ions by adding Cl2 or chlorine water into a bromide ion solution, followed by the addition of CCl4 and mixing. So we have two layers, and we observed when you do this, the CCl4 layer. What happens to CCl4 layer? It will turn orange. CCl4 layer will turn orange. Right. What about iodide ions? If you add CCl4 to an iodide ion solution and then added it with chlorine water, we would observe that the CCl4 layer will be turned, or we will observe that it turns purple. Right, so when we were doing this experiment in the lab, we saw CCl4 layer turned orange when it comes to bromide ion solution, and when it comes to iodide ion solution, CCl4 layer turned purple. Now students, what will happen instead of using chlorine water if we use bromine water? And then followed by the addition of CCl4. Will there be a specific color change? Yes, students, in this case, since we are adding bromine directly into our reaction mixture, we have, if you draw the reaction mixture, you will have on the upper layer, it will be a mix of bromide ions added with our bromine water. So Br2 will be there in the aqueous layer, and the bottom layer will be our CCl4 layer, carbon tetrachloride organic layer. So when you add bromine is now added to the aqueous layer. The bromide ions in the aqueous layer won't react with bromine water. However, since bromine water carries bromine in it, when we add bromine water over here and when we mix it with the organic layer, some of the bromine molecules will go into the CCl4 layer and it will turn that layer into an orange color. So you can say CCl4 turns, or CCl4 layer will turn orange. So this is a very clear observation, students. And then when it comes to the next observation, iodide ions. When you add bromine water to iodide ion solution, we learned about this in the theory part. If we add bromine molecules or bromine water into iodide ion solution, iodine will be formed, while reducing bromine molecules into bromide. So therefore, the iodine that is formed will dissolve in CCl4 layer. So the CCl4 layer will turn, purple. It will turn purple, students. So can we use bromine water and CCl4 to identify uh, the presence of bromide ions and iodide ions separately? The answer is yes. Separately, you can identify the presence of bromide and iodide with the use of bromine water, because we can see very clear two different observations. In the presence of bromine, iodide ions will get oxidized to form iodine, and iodine will dissolve in CCl4 layer, and the CCl4 layer will change its color from clear to purple. So this is a very clear observation that we can use to identify the presence of bromide ions and iodide ions separately. But over here, they say Br2 dissolved in toluene. This is not bromine water. We are using Br2 dissolved in toluene. So we are not getting bromine water, and on the other hand, we are not getting CCl4. But bromine is introduced into the system. So bromine then can react with iodine to form iodide ions to form iodine. It is not going to be a problem. However, although bromine is there in the system now, can toluene act as a replacement for CCl4? That should be your question. And the answer is yes. Toluene is an organic solvent. So when carrying out this experiment, CCl4 is not the only solvent you can use, organic solvent you can use. CCl4 is carbon tetrachloride. Apart from using CCl4, you can use chloroform. Chloroform can be used. CHCl3 is the formula. Or else you can use benzene, right? Benzene can be used, which is C6H6, or in other words, if you want to draw the structure, this is benzene. Or else you can use toluene. Or also known as methyl benzene. So basically, methyl benzene or toluene is this. So students, either one of these organic solvents can be used. So if you have Br2 dissolved in toluene added to a potassium iodide solution, then what happens? Potassium iodide aqueous solution is there. Toluene would act as your organic layer, and it will sink to the bottom as toluene is going to have a high density. And then on top we have water, and in the aqueous layer you will have your iodide ions, and the bromine from the toluene will come into contact with the iodide ions, and bromine will turn into bromide while turning iodide ions into iodine. So then the iodine molecules that are formed will dissolve in toluene and make that organic toluene layer purple in color. So instead of having CCl4, we can use all of these substitutes. Chloroform or benzene or toluene can be used in place of chloroform. So therefore, the answer to this question is 3. Very clearly, the answer to this question is 3. Now we move on to the next question. So this question asks, suppose you are not provided with hydrogen and other metallic elements in the lab. Assume chlorine, bromine and iodine and other general chemicals are provided. And how would you show under these conditions that the reactivity of halogens change from chlorine, bromine to iodine? So chlorine being the most reactive, iodine being the least reactive. How are you going to show that chlorine, bromine and iodine reactivities vary this way? The simple answer is the same example that I was talking about earlier a little while ago. That is, we observe the fact that, or we do see that chlorine Cl2 is capable of displacing bromine. So out of these two, you can very clearly see at that point, chlorine is more reactive. Because chlorine is capable of displacing bromide ions as bromine, chlorine has more of an oxidizing power, so it is acting as a very strong oxidizing agent in this particular instance and is oxidizing bromine. Then, if you take a look at bromine, if you add bromine to an iodide ion solution, we discussed this equation as a special test in theory parts. So iodine will be displaced when bromine is added to iodide ion solution, and bromine will turn into bromide. So students, it's very clear that bromine was more reactive than iodide. Otherwise, iodide will not be displaced by bromine. So this is the main explanation to this question, but you need to show it, right? You need to show it through an experiment. So what could be the experiment? You can say, take a test tube and into the test tube take sodium bromide solution, NaBr solution, and add 10 cubic centimeters of carbon tetrachloride, our nonpolar organic layer, and to this you can mention add chlorine water. So upon addition of chlorine water, what will happen, students? Upon addition of chlorine water, you will observe that the CCl4 layer turns orange. This indicates Br2 was formed. So this is one test that you can do to show that chlorine is more reactive than bromine, or chlorine is more oxidizing than bromine. That is why chlorine was able to oxidize bromide ions into forming bromine molecules. So we have, with that observation, you can establish the fact that chlorine's reactivity is greater than bromine's. That part is established. To show that bromine is more reactive than iodine, we can take a solution like potassium iodide aqueous solution into a test tube, and we can add carbon tetrachloride just like we did in the previous step. So basically we are repeating the setup of the chlorine water test, but instead of adding chlorine water, in this case what are we adding? We will be adding bromine water. We'll be adding bromine water. So when we add bromine water, students, what will happen? We will see that in this case the CCl4 layer turns purple. Indicating what? Indicating that I2 has been formed. And why did I2 get formed? Because bromine was capable of oxidizing the iodide ions in the medium to form iodine gas. So that means bromine is more reactive than iodine. That is why iodide ions were displaced as iodine by bromine. So this established the fact that bromine is more reactive than iodine. So how do we show in the lab? In the lab, you can indicate the reactivity of bromine or chlorine, bromine, and iodine through these two experiments. Chlorine is capable of displacing bromine, and bromine is capable of displacing iodine. So these two reactions will give you the desired answer here. The question asks us how we can show that chlorine is the most reactive out of chlorine, bromine, and iodine, and then bromine is the most reactive, and finally iodine is the least reactive. So that answer, that particular order can be observed when we carry out this particular two reactions. So students, in your answer you need to mention how these tests are carried out. It's very simple. You can say take a small volume of sodium bromide into a test tube, add 10 cubic centimeters or equal volume of carbon tetrachloride, and then add chlorine water and observe the color change of the organic layer. The color of the organic layer changes to orange. This indicates bromine was formed. This means that bromine was displaced by chlorine, indicating chlorine is more reactive than bromine. And then in the next part, we will again outline the steps. We will say, then take a small volume of potassium iodide solution and add equal volume or 10 cubic centimeters of carbon tetrachloride into the same test tube. And to the aqueous layer, add a small volume of bromine water. And then shake the test tube. You will see the carbon tetrachloride layer turning to a purple color. This will indicate that iodine has been displaced. So who displaced iodine? So you have to write iodine was displaced by bromine, indicating bromine is more reactive than iodine, or bromine is having more oxidizing power than iodine. This establishes the fact that bromine is more reactive than iodine and chlorine was more reactive than bromine. So therefore the order is chlorine, then bromine, then iodine. So students, that is how you would answer this question. Now students, with this we conclude our discussion. So in this experiment we discussed the theory parts revolving around identification of halides, and then we went into the lab and observed all of these chemical reactions and the observations revolving around these reactions. And finally, we discussed some questions to give you an idea of how to answer questions revolving around practical 13. So students, I hope that you learned how you can identify different halide ions like chloride, bromide, iodide ions when they are present in aqueous mediums. And I hope if you are faced with a question like this, that you'll be able to answer them with ease from now onwards. So with that, I will conclude today's practical, and I will see you again in the next one.